The collision of two galaxies is an ordinary phenomenon in the evolution of galaxies. It occurs when two galaxies collide at sufficient speed to merge. The gas and dust of the two galaxies will then interact. The interstellar medium is disturbed and heated. This shock can trigger a starburst, also known as a starburst galaxy, in one of the two galaxies. This phenomenon generates an exceptional rate of star formation in one of the galaxies. These bursts are temporary, because if the rate of star formation were to remain so high, the reservoirs of star-forming gas would be completely dissipated much faster than the dynamic lifetime of the galaxy. The stars in the two galaxies, meanwhile, generally don't collide with each other, as the distances between stars. A starburst is generally defined by three factors: the star formation rate, which is the rate at which the galaxy will convert gas into stars, the amount of gas available to form stars, and the comparison between the star formation period and the age of the galaxy. For a starburst to occur, a large quantity of molecular gas must be concentrated in a small volume. This usually occurs during galaxy mergers. Categorizing the various starbursts is not straightforward, as not all galaxies share the same specific characteristics. Starbursts can occur in the galactic disk or be scattered throughout the galaxy. Nevertheless, astronomers are currently discussing a number of classes. The subtypes of starbursts currently defined are blue compact galaxies, infrared luminous galaxies, and Wolf-Rayet galaxies. Compact blue galaxies have low mass and low metallicity. Dust-free, they contain a large number of relatively young hot stars. As a result, they are luminous in the blue and ultraviolet. Astronomers initially thought these galaxies were young, but old stellar populations have been found in a number of them. In addition, the majority of compact blue galaxies show evidence of recent interactions. Infrared, luminous galaxies are characterized by extremely high dust concentrations. They emit a red color because the ultraviolet radiation they emit is absorbed by dust and re-emitted as infrared. Most of the infrared luminous galaxies observed show a double-core system. This suggests that star formation may have been triggered by galaxy mergers. In Wolf-Rayet galaxies, the majority of bright stars are Wolf-Rayet stars. These hot stars, with masses equivalent to several tens of solar masses, will start expelling matter in the form of high-speed stellar winds during a brief phase. A starburst has a large gas reserve. Collision with another galaxy triggers the starburst itself. Inside the starburst, the environment is extreme. Massive star formation generates large quantities of gas. One of the most famous starburst systems is the Antennae galaxy. The Raven constellation is one of the 48 constellations listed by the astronomer Ptolemy. It lies close to the constellation Virgo to the north and east, Hydra to the south, and Cup to the west. The Raven constellation has few bright stars. Its four brightest stars are Gamma, Beta, Delta, and Epsilon. Gamma, with a magnitude of 2.59, remains the brightest. These four are easy to spot in the night sky, as they form an unusual quadrilateral. However, the most striking celestial objects in this constellation are not these stars, but two galaxies that are currently on a collision course, the Antennae galaxies. Also known as NGC 4038 and NGC 4039, the antenna galaxies are an emblematic example of galactic collision. While pairs of interacting galaxies are quite common in the universe, it's rarer to witness the spectacle offered by NGC 4038 and NGC 4039. According to scientists, the collision began 600 million years ago. The antennae galaxies were originally two spiral galaxies. NGC 4038 is very large and lies at a Hubble distance of around 95.2 million light-years. It is also defined as a star-forming galaxy. It has an exceptional rate of star formation compared with other observed galaxies. This phenomenon represents just one stage in the life of a galaxy, and is certainly due to the interaction with NGC 4039. The phenomenon is therefore limited in time. The interaction of the antenna galaxies in the night sky is a veritable firework display, illuminating thousands of nebulae and young star clusters. It's a spectacle of unspeakable beauty. The arms of the galaxies were deformed and the cores brought close together. The impact sent out two immense jets of stars and gas, earning this celestial duo the nickname the Antennae. With a 100mm aperture, it's possible to observe the galaxy duo, which appears as a diffuse spot with no detail. When viewed through a 200mm telescope, the dual nature of the object becomes clear. Its shape takes on the appearance of a V elongated towards the west. But it's only when you use 300 to 400mm instruments that the spectacle becomes striking. The two antennae galaxies form a magnificent, asymmetrical boomerang. NGC 4038 to the north represents the brighter, more curved part, while NGC 4039 to the south is thinner. Astronomers believe that within 400 million years these two galaxies will have merged. For us, this gigantic timescale is nothing compared to the lifetimes of these stars. This collision could give rise to a larger galaxy, perhaps of the elliptical type. The nearest ultra-bright infrared galaxy is ARP 220. It is located around 245 million light-years from the Milky Way, in the constellation of Serpent. ARP 220 is the result of the collision of two galaxies that are currently merging into one. ARP 220 radiates mainly in the infrared. Most of its luminosity comes from the intensive formation of young stars, since it is a star-forming galaxy. Scientists have observed over 200 stellar clusters at the heart of this galaxy, some reaching masses of the order of 10 million solar masses. ARP 220 has an active galaxy core. This core is characterized by a compact region at the heart of the galaxy. Its luminosity is higher than average and not of stellar origin. In theory, it results from accretion by a supermassive black hole. The Whale constellation is the fourth largest constellation in the sky. Its best-known stars are Mira and Difta. Within this constellation lies the ARP 147 system, also known as the Ring Train. This pair of colliding galaxies lies 440 million light-years from Earth. The Ring Train perfectly represents the most spectacular effects of galaxy collisions. The two galaxies making up the pair are considered special galaxies in that they are neither elliptical, spiral, barred spiral, nor lenticular. They are, however, regular in shape. The two galaxies are shown, one in profile, evoking the number 1, and the other from the front, appearing to represent the number 0. Together they form a gigantic 10. This extraordinary figure in the sky is the result of an extremely violent collision. The galaxy on the left, representing the number 1, has smashed right through the galaxy on the right, representing the number 0. In the same way that a pebble emits a wave when it comes into contact with water, the collision created a wave at the point of impact. This density wave traveled outwards through the affected galaxy, colliding with the star's gas and dust as they tumbled towards the center, under the effect of an increased gravitational force. As a result of the collision, the high-temperature matter clumped together, stimulating the formation of young stars. A red spot can be seen at the bottom of the right-hand galaxy forming 0. This is probably the remnant of the galaxy's nucleus after the collision. Made up of around 50 individuals, the local group is a very modest cluster in which our galaxy, the Milky Way, lies. Nevertheless, its evolution has been as tumultuous as that of larger galaxy groupings. Based on the stigmata found on the Andromeda galaxy, also known as M31, numerical simulations have attempted to reconstruct its past. At present, M31 is the only galaxy in the local group larger than the Milky Way. 5 billion years after the Big Bang, the local group is made up, in addition to the future Milky Way, of 2 rather large galaxies, one of which is 4 times more massive than the other. Their relative proximity generates a mutual attraction that brings them closer together, until they inevitably collide 4 billion years later. The merging of these 2 galaxies gives rise to the Andromeda galaxy. The distances between the stars of the 2 galaxies are so great that another head-on collision is ruled out. Tidal forces create a gigantic trail of stars. Part of it returns towards the larger galaxy, the result of the ongoing merger, while the other part escapes the latter's grasp and gathers into 2 dwarf galaxies, known as the Magellanic Clouds. Their speed is such that they soon find themselves close to the Milky Way. Supernovas are spectacular events marking the end of the evolution of a massive star. During these gigantic explosions, the energy released in a few seconds is comparable to that emitted by a star throughout its lifetime. The phenomena triggering these explosions vary, according to whether the star belongs to a binary system or to a single star. In the latter case, a supernova explosion will only occur if the binary system's companion star is a white dwarf. Under certain conditions, the white dwarf is gravitationally bound to its companion star, absorbing matter from the latter's surface layers. The captured material falls onto the white dwarf and heats up. When it exceeds the mass limit at which a nova is formed, nuclear reactions are set in motion until it is destroyed. In the case of an isolated star, the star itself explodes once all internal nuclear fusion cycles have taken place. Gravity then takes over, and the star contracts very rapidly. The resulting heating triggers uncontrolled nuclear reactions in the core. An explosion occurs, releasing enough energy to destroy the star. The explosion leaves behind a trace called supernova remnant. This is an expanding cloud of gas. Astronomers identify supernovas by their characteristic light curve. They exhibit a rapid increase in luminosity that lasts several days. When this luminosity reaches a maximum, it stabilizes for around 10 days. It then decreases discontinuously, followed by a steady decline. Interpretation of the light curve enables us to study the evolution and dynamics of the explosion. Because of their extreme brilliance, supernovae are one of the favorite objects of astronomy enthusiasts. And it's thanks to them that around 50 supernovas have been discovered every year since 1990. Several supernovas have left their mark on the history of astronomy. On February 24, 1987, Canadian-born astronomer Ian Shelton set out to take long-pause photographs of the Large Magellanic Cloud, a dwarf galaxy close to the Milky Way, visible from the southern hemisphere. While developing his photographs, he was surprised by the presence of a new star. After consulting several colleagues, he discovered that the star had also been seen by others. The first traces of the explosion to reach Earth were carried by neutrinos, which are difficult to detect particles emitted rapidly, in very large numbers, shortly before the star's increase in luminosity. SN 1987A was the first supernova explosion of the 20th century to be observed by the naked eye under optimal observing conditions. It provided crucial data for understanding the mechanisms of these stellar explosions. The general principles governing the supernova phenomenon have been confirmed. Studies clearly show that 99% of the energy emitted by supernovas is in the form of neutrinos. But for the first time in 1987, thanks to the supernova explosion, neutrino emission was observed instantaneously. When the star's core collapses under the effect of gravitation, electrons merge with protons to form neutrons and neutrinos. The latter interact very little with matter and are immediately released. Another feature of SN 1987A is that the star that gave rise to it was a blue supergiant. The presence of 3 gas rings around the supernova made it possible to understand that the star had evolved from a red supergiant to a blue supergiant around 20,000 years before the explosion. This progenitor star is called SK 69202, or Sandelic 69 degrees 202A. It was born 10 million years ago with a mass 20 times that of the Sun. Astronomers were surprised that it was a blue supergiant rather than a red one, as it was suggested at the time that only stars in the red supergiant stage evolved into supernovas. Today, the supernova afterglow remains the focus of numerous observations, even if the search for the compact residue has so far been unsuccessful. Thanks to numerous instruments on the ground and in space, the supernova has been observed continuously, both in terms of electromagnetic radiation and by neutrino detectors. The phenomenon occurred at a distance of around 51.4 kiloparsecs from our planet. In May 1987, it reached its maximum brightness with an apparent magnitude of around +3. Supernova 1993J occurred in galaxy M81 in 1993. It was discovered by a Japanese amateur astronomer and was one of the brightest supernovas of the 20th century. Its ancestor has been identified as a K-type supergiant star, characterized by an excess of ultraviolet light, which may be due to the surrounding hot stars or a hot binary companion. SN 1572, also known as Tycho's supernova, is a supernova in the constellation Cassiopeia, 7,500 light-years from Earth. It owes its name to the Danish astronomer Tycho Brahe, who first observed it on November 11, 1572. On that day, it appeared much brighter than Venus, with an apparent magnitude of -4. It wasn't until March 1574 that its brightness dropped below the threshold of visibility to the naked eye. This supernova became one of the most famous events in the history of astronomy, since it contradicted the Aristotelian theory of the inalterability of the cosmic world. Indeed, since ancient times, the world beyond the moon had been considered unshakable. For scientists of the time, it was only between the Earth and the moon that new celestial objects could appear. Tycho Brahe's discovery implied a new object much further away. Over the course of months of observation, he also discovered that the object had not changed position relative to the fixed stars, and could therefore not be a planet, but another star. In 1573, Tycho Brahe published his discovery, calling it a new star. This revolutionary expression turned astronomy on its head. It led to the development of better astronomical classification catalogs and improved observational instruments. The supernova's progenitor star was probably a dwarf that had drawn in matter from another companion star until it exploded. Type 1 supernovas, like SN 1572, do not involve the formation of extraordinary nebulae. That's why its faint afterglow was only discovered in the 1960s. Thanks to the Chandra Space Telescope, astronomers were provided with astonishing images of Tycho's supernova. These showed lumps in the remains of the star, as if several ignition points had existed within the supernova. The explanation is that SN 1572 underwent an asymmetric explosion. The explosion produced a large cloud of expanding debris. A thin blue line representing ultra-high energy electrons can be seen around the perimeter. The dust formed is ejected into the cosmos. Numerous other stars adorn the supernova's vicinity, like sparkling white diamonds. SN 1604, also known as the Kepler supernova, occurred in the Milky Way in the constellation of Ophiuchus in 1604. It is a type 1A supernova, or thermonuclear supernova, resulting from the explosion of a white dwarf. In most cases, the latter captures the matter of a companion star until it reaches critical mass and explodes. In the case of Kepler's supernova, however, it appears to have been triggered by the merging of two white dwarfs. As there are no bright stars in the vicinity of the central region of the supernova's remnants. SN 1604 was observed by German astronomer Johann Kepler and was visible to the naked eye for over a year. Kepler was not the discoverer of the supernova, but it was he who carried out the most detailed research on the star. He wrote about it in his book, Sur la nouvelle étoile dans la pied de Ophiuchus, On the New Star in the Foot of Ophiuchus. This supernova lies at a distance of 20,000 light-years from our planet Earth. Its relatively low position on the horizon and declination of -21 degrees could have made it difficult to detect. But certain circumstances were favorable to its discovery. SN 1604 lies in a region where the planets of the solar system circulate. In October of that year, Jupiter, Mars, and Saturn were located in this very zone. What's more, with the Sun at the same time located around 60 degrees west of this region, the sky was easily observable in the early hours of the night. What's more, Tycho Brahe's discovery some 30 years earlier had sparked a great deal of interest among astronomers in observing the night sky. Today, NASA astronomers report that some debris from the explosion is still moving through space at speeds of up to 37 million kilometers per hour. The average speed of the clusters studied is around 16 million kilometers per hour. The four fastest clusters in SN 1604 are all heading in the same direction and have a similar chemical composition. This may mean that the debris is coming from a single layer of the progenitor star. These velocities have already been observed in supernovae and other galaxies, but only just after their explosion. In the case of SN 1604, the displacement of its remnants continues unabated, even 400 years later. Astronomers have yet to explain this phenomenon, but several theories have been suggested. The explosion could have been so violent that the material was ejected at very high speed, or the white dwarf's environment is lumpy, and the debris made its way along low-density paths without being slowed down. SN 1054, also known as a supernova of the year 1054, is famous for the afterglow it left behind after the explosion, known as the Crab Nebula. It is one of the most studied objects in the sky. The supernova was observed in 1054 and documented by Chinese and Arab astronomers. Numerous written sources attest to the explosion of a star in 1054. At the time, in China, transient stars such as comets, novas, or supernova explosions were called guest stars. Several accounts in official archives of events during certain dynasties relate this phenomenon in 1054. 3 other Japanese texts, individual chronicles, also mention this guest star at the same time. In the Arab world at the time, astronomers were interested in cyclical phenomena, whereas supernova explosions were considered to be atmospheric phenomena. Nevertheless, there is a doctor's account of a spectacular star appearing in the sky. All report that in July 1054, a star began to shine so brightly that it exceeded the brilliance of Venus. It remained visible in daylight for 3 weeks, and in the night sky for almost 2 years. 7 centuries later, in 1758, the famous Charles Messier searched assiduously for Halley's Comet and confused it with a small nebula in the Taurus constellation. To avoid further confusion, he decided to create a catalog of diffuse stars and assign the number 1 to this star. In 1928, Edwin Hubble made the connection between the Chinese astronomer's guest star and the Messier 1 nebula, the expanding cloud of gas released by the supernova of 1054. It's nicknamed the Crab Nebula. This nebula continues to grow at a speed of 1,500 kilometers per second, or 930 miles per hour, and will dilute in space over the coming millennia. Within the nebula remains the compact residue of the exploded star, the Crab pulsar. The pulsar is less than 1,000 years old. It generates electromagnetic radiation 100,000 times more intense than the Sun. This is what makes the central part of the Crab Nebula so bright. The nebula and pulsar form one of the most studied structures outside the solar system, as both are among the brightest objects in their respective categories. What's more, the date of the explosion is well known. SN 1054 is the most famous supernova in the history of astronomy. In winter in the northern hemisphere, it can be observed through a small telescope and appears as a pretty gray blob against the stellar background of the Milky Way. Supernova 2014J occurred in galaxy M82 in January 2014. It is a Type 1a supernova, and the closest to it discovered in over 40 years. To date, it remains the brightest supernova observed in the Cigar Galaxy for decades. It has been extensively studied in different wavelengths due to its unusual brightness and proximity. Far less spectacular than Type 2 supernovas, which are the endpoint of massive stars, whose remnant is usually a neutron star, Type 1a supernovas are produced by the explosion of much smaller stars, known as white dwarfs. Their explosions are said to be thermonuclear. At the end of the explosion, all that remains in space is a gigantic jet of particles known as afterglow. The supernova was discovered on January 21, 2014 by chance, while astronomer Steve Fosse was training his students to use a small telescope at the University of London Observatory. The scientists simply wanted to take advantage of a brief gap in London's cloud cover. He and his students then noticed a bright new star in the images taken of the Cigar Galaxy. The discovery was reported to the Astronomical Union's Central Astronomical Telegram Office, which confirmed that they were the first to spot this supernova. At the time of discovery, the supernova was 14 days from its maximum light, suggesting that it would become brighter over the following 2 weeks. It continued to get brighter until January 31st, when it had an apparent magnitude of 10.5. Quasars are the brightest sources of light in the universe. The word quasar comes from an English abbreviation meaning source of quasi-stellar radio radiation. These are extremely distant stars that look like very bright stars when observed through a telescope, but are actually examples of active galactic nuclei. Their impressive energy comes from the accretion of matter by rotating supermassive black holes that can contain millions to billions of solar masses. The black holes that sit at the center of galaxies are of an altogether different caliber to those produced by stars. While the latter sometimes reach the mass of the Sun, galactic black holes are millions, even billions of solar masses. The luminous power emitted by quasars can reach 10,000 times the total luminosity radiated by the hundreds of billions of stars in a galaxy the size of our Milky Way. However, most galaxies are not the site of such a violent outburst. Quasars are thought to gain power through the accretion of matter around supermassive black holes in the nuclei of these galaxies. No other mechanism seems capable of explaining the immense energies released and their rapid variability. But some phenomena remain unexplained to this day. For example, some relatively quiet galaxies seem to suddenly become quasars in just a few months. The remarkable luminosity of quasars is used as a tool for probing intergalactic space, right up to the limits of the observable universe. Before reaching our telescopes, the photons emitted by quasars may encounter tenuous clouds of intergalactic gas on their billion light-year journey. Quasar absorption systems provide additional structural information to that provided by the distribution of galaxies. The growing number of known quasars, with their absorption spectra, enables more detailed statistical studies of the distribution and properties of intergalactic gas clouds and their relationship with dark matter and existing or forming galaxies. Absorption systems can be used to probe precise moments distributed throughout the history of the universe, but also to address essential issues in cosmology and even physics. The first quasars were seen as early as the late 1950s, and today there are over 100,000. Quasar 3C273 lies at an astronomical distance of 2.44 billion light-years, 1,000 times further away than the Andromeda galaxy. It is located in the constellation Virgo. According to Hubble's law, and given its distance, This quasar is moving away at almost 50,000 kilometers per second, or 31,000 miles per second. The black hole at its center needs the equivalent of several hundred times the mass of the Sun per year to feed itself. It discharges some of this matter in the form of an immense jet. When it no longer has enough energy to feed itself, its host galaxy will revert to an ordinary star, and its luminosity will diminish. If there's one object in the universe renowned for its unprecedented violence, it's the quasar 3C186. This double quasar emits waves in all domains of light. It lies in the Lynx constellation, more than 8 billion light-years away. 3C186 lies at the heart of the galaxy, PGC 2817581. It has several special features. Its central light is offset by around 35,000 light-years from the center of the galaxy. This is due to the interaction between 3C186 and the second black hole inside it. The impact of these two supermassive black holes disrupts the galaxy, breaking it up and scattering its stars. The interaction between the two black holes is thought to have taken place 5 million years ago. Astronomers estimate that 3C186 will leave the galaxy in around 20 million years. The result will be two supermassive black holes merging to form a black hole with a mass equivalent to 1 billion solar masses. The Earth has been hit by numerous asteroids. These collisions have played a major role in the history of its formation and evolution. Some 9 billion years have passed since the Big Bang. The local supercluster contains over 10,000 individuals. On its periphery, the local group is made up of some 50 galaxies, including the Milky Way, one of the largest. The Milky Way has a thin disk of stars and gas. This highly diluted gas concentrates in a few places, in much denser spirals. These interstellar clouds are opaque with molecules and grains of dust. One of them wanders proudly 27 light-years from the center of the Milky Way. Then, a fragment of this nebula collapses in on itself. The contraction transforms the globule into a protostar, and its energy into radiation. At its heart, the temperature rises so high that thermonuclear reactions cause hydrogen to fuse. A star is born, but not just any star, our Sun. Before its final contraction, the protostar is surrounded by a disk of gas and dust, which then divides into countless smaller bodies. Some agglomerate into larger structures. Matter spinning too fast to join the Sun in formation takes the form of a disk made up of gas, dust grains, and tiny aggregates of solid matter. The grains gradually stick together until they agglomerate into blocks. Under the effect of gravity, bodies over 1 kilometer in length are formed. The largest of these absorb everything within their sphere of influence. Planetary embryos are born. Their mass increases with distance from the Sun. Below the ice line, the environment is gradually emptied of gas, and the planetary embryos see their orbits lengthen to the point where they can cross each other. Violent collisions ensued, leaving only 4 of the planets, including Earth, intact. Barely scratched out of the ground, the Earth is already experiencing an eventful life. Our planet has cleaned up its orbital zone. The only exception is the 2 Lagrange points, L4 and L5, in the Earth-Sun system, which provide shelter for planetesimals attracted to the Earth during its formation. Point L4, for example, shelters a planetary embryo that continued to develop until it reached the size of today's Mars. Its name is Theia. Having reached too great a mass, Theia became unstable and escaped from its L4 equilibrium point. It then orbits the Sun until it collides with the Earth. Theia is totally shredded. Its pieces scatter all around. Its core, mainly iron, is buried in the heart of the Earth. 24 hours after impact, our future planet is surrounded by a disk of light rock from the two planetary mantles that collided. After a few years, these rocks agglomerate to form a new celestial object 20,000 kilometers or 12,500 miles from the Earth, which gradually moves away to become its satellite, the Moon. At first glance, this cosmic collision seems no more exceptional than any other. And yet, by giving the Earth such a large satellite capable of stabilizing its axis of rotation, this collision is paradoxically an essential event in the future evolution of life. The Moon plays a very important role in the existence of life on Earth. It exerts a major influence on the weather, the migrations of certain animals, the Earth's magnetic field, and in many other areas. It is also responsible for the 24-hour day. The Earth's tilt is kept stable by the Moon's gravity. If it weren't for the Moon, our planet would move up and down during its rotation. And if such wild movements were to take place, wind and clouds would move faster, and weather conditions would be extremely harsh and much less conducive to life. The phenomenon of the four seasons is also due to these changes in the Earth's rotation and axis. Without the Moon, the Earth would rotate on its axis in 8 hours instead of 24. The Moon's gravity slows down the Earth's movement, with enormous repercussions for the evolution of life on Earth. If a day lasted 8 hours, animal species would have had to adapt to rapid temperature changes and would certainly have evolved very differently. During the Moon's first days, solar winds were much more violent. At that time, the Moon was closer to the Earth, and its magnetic field was sufficient to protect its atmosphere and act as a shield against solar winds. If the Earth had no atmosphere, life as we know it today would not be possible. It contains the oxygen we breathe and protects us from ultraviolet rays and cosmic rays. The effect of the Moon's and Sun's gravity on the Earth slightly deforms the planet from front to back. This is what we call tidal forces, which cause ocean tides. Tides probably propelled the first forms of marine life onto land. Tides may also have influenced the Earth's plate tectonics. It is thanks to seismic activity that the planet's surface was able to cool and become habitable. "4 billion years ago, large-scale meteoric and cometary impacts hit the terrestrial planets. It was during the Apollo 15, Apollo 16, and Apollo 17 missions that this theoretical period in the history of the solar system was brought forward. The landing sites for these missions were established close to the great impact basins of the Sea of Rain, the Sea of Nectar, and the Sea of Serenity. Lunar rock samples were collected, and analysis on Earth revealed that their age ranged from 3.8 to 4.1 billion years, a relatively short period. These data were compared with the dating of other lunar meteorites recovered on Earth. Due to erosion, impact marks of ancient origin are very rare on our planet. Although this has long been interpreted as proof that the Earth's surface remained liquid for a long time, it would appear that in reality, the solidification time was much faster, and that the youth of the Earth's crust is due to the theory of the late Great Bombardment. At the start of the solar system's formation, the four giant planets were much closer together than they are today. Uranus is the furthest from the Sun and lies close to the inner edge of a planetesimal-rich disk. Barely 600 million years after the formation of the solar system, the gas giant planets began to migrate due to gravitational interactions with the famous small objects that remain at the inner edge of the disk. Saturn, Neptune, and Uranus are moving strongly inwards, and Jupiter more moderately. Jupiter's rotation period around the Sun is half that of Saturn. This movement completely destabilized the solar system, and collisions between small bodies and the terrestrial planets increased. It was the beginning of chaos. Saturn was pushed back into its final orbit by Jupiter and collided with Neptune and Uranus. The latter two are expelled into much more elongated orbits. They plunge into the planetesimal-filled disk, ejecting thousands of planetesimals far from their original orbits. For the most part, these small bodies fly outside the solar system, giving rise to the Kuiper Belt, among others. But some of them head inland. The four terrestrial planets, as well as the Moon, are the victims of numerous brutal impacts. The Earth is said to have been hit by 22,000 giant meteorites. Some asteroids were larger in diameter than France. The oceans that covered the Earth's surface were partially vaporized. Mercury, the Moon, and Mars bear the scars of this massive bombardment. On Mars, the Hellas Planitia impact basin has been linked to the Great Lake bombardment by analysis of lunar samples. The basin measures around 2,200 kilometers, or 1,400 miles in diameter, and 9,500 meters, or 31,000 feet in depth. It is the largest impact structure on Mars visible from Earth. The basin appears as a bright area due to the high albedo of the dust constantly stirred up by the winds. The Hellas Planitia basin is surrounded by relief created by the impact. For over 1,000 kilometers, the terrain was raised. To the west, the edge of the basin is marked by a mountain range. In places, it reaches an altitude of 2,000 meters or 6,500 feet. To the east, the edge is marked by valleys, representing the beds of large rivers that have now dried up. Water was abundant in the impact basin. On the planet Mercury, the Caloris Basin is the most massive meteor crater known to date. It is located at one of the planet's two hot poles. Measuring around 1,550 kilometers, or 960 miles in diameter, it was formed by the fall of an asteroid with a diameter of around 150 kilometers, or 93 miles. The basin is surrounded by mountains that rise to almost 2 kilometers, or 1 mile in height. Its floor is filled with cooled lava, reminiscent of lunar pools. For some 1,000 kilometers, or 620 miles, the material ejected by the impact forms rings surrounding the basin. The impact that formed the Caloris Basin is thought to have triggered volcanic activity on Mercury. The impact is also thought to have released heavy elements such as sodium and potassium from the planet's mantle. Being around 130 kilometers or 80 miles deep, elements could have been brought up from the mantle during readjustment movements. On the Moon, the Mer Orientale and the Mer des Pluies are basins that would also have been dug during the Great Lake bombardment. The Mer Orientale is a lunar sea formed by the impact of a meteorite, which raised the mountains bordering the crater. It is one of the Moon's most impressive structures. with a diameter of around 900 kilometers, or 560 miles. Two mountain ranges encircle the Mer Oriental: the Montes Rook, measuring 700 kilometers, or 430 miles in diameter, and the Montes Cordillera, measuring 900. The Sea of Rains is a sea found on the visible side of the Moon, formed when liquid lava filled a giant pre-existing impact crater, called the Basin of Rains. The latter is surrounded by three mountain rings, each composed of several mountain ranges. For some 800 kilometers or 500 miles, an area is covered by ejecta, forming a region of numerous reliefs. Asteroid impacts are common phenomena in the solar system. 160 million years ago, a collision between two large objects in the asteroid belt produced numerous fragments, known as the Baptistina family. The first body is located on the inner edge of the asteroid belt, just over 2 astronomical units from the Sun. Despite the fact that its growth is limited by the disruptive presence of Jupiter, it boasts a diameter of 170 kilometers or 100 miles, a very respectable size. It is one of the largest asteroids in the main belt. The second body involved in the collision is another asteroid, 60 kilometers or 37 miles in diameter. Its orbit is similar to that of the first asteroid. One day the two collide. The impact occurs at a speed of 3 kilometers per second, or 1.8 miles per second. It was so violent that the two asteroids were reduced to a dust of debris, which aggregated again to form a family of objects with similar orbital characteristics. This is the Baptistina family. This asteroid family comprises some 2,500 known members. Many years ago, we thought that some of them were responsible for remarkable cosmic collisions, such as the one that caused Tycho's crater on the Moon, or a direct collision with the Earth 66 million years ago. However, data from the Wide Field Infrared Survey Explorer in 2011 challenged this hypothesis, suggesting that the Baptistina family had in fact formed much more recently than previously thought, as recently as 80 million years ago. Consequently, the origin of the impactor that caused the extinction of the non-avian dinosaurs remains an unsolved mystery. Further study and exploration of the asteroid belt may one day unravel this mystery and help us understand the forces at work that triggered these impacts. Asteroids can undergo an effect that affects their rotation on themselves in the presence of radiation. When the object's face is illuminated by the radiation source, it receives energy. After half a revolution, this same face then goes into shadow, radiating outwards the energy it has previously received. The result is a very slight thrust exerted on the object, depending on its shape and surface condition. This is known as the Yarkovsky effect, named after the Russian engineer who discovered the phenomenon. Many individuals are then disrupted by Jupiter and the other planets. They find themselves injected into orbits that lead them to cross those of the Earth and Moon. 108 million years ago, an asteroid measuring 10 kilometers or 6 miles in diameter swung low over the Moon's western horizon and collided with it. The impact creates a huge impact crater called Tycho. This sends thin cracks across the Moon's southern hemisphere, extending to over 1,000 kilometers or 620 miles in all directions. The crater is located in the southern lunar mountains. It has well-defined contours, and its interior is characterized by a high albedo. The crater's diameter is 82 kilometers, or 50 miles, and its rim rises to 4.7 kilometers, or 3 miles above floor level. At that time, from Earth, it was the dinosaurs who witnessed this cosmic collision. Little do they know that they will be the next victims of these cosmic events. The Chicxulub crater is the most famous asteroid impact on Earth. It occurred around 66 million years ago in Mexico's Yucatan Peninsula and is associated with one of the world's largest mass extinctions. The impacting asteroid measures around 10 kilometers in diameter. On contact with the Earth, it formed a crater 180 kilometers, 112 miles in diameter. This suggests an explosion power several billion times that of the Hiroshima bomb. The crater basin is covered by about 1,000 meters, or 3,300 feet of limestone. It extends under the mainland and the Gulf of Mexico. Scientists are trying to explain what really happened during the impact that caused the demise of those who reigned supreme at the time, the dinosaurs. At the time, these gigantic, majestic animals had dominated the planet's animal ecosystem for 165 million years. They are the most imposing creatures the Earth has ever sheltered. Dinosaurs are very diverse and are found all over the planet. An asteroid in a region between the orbits of Mars and Jupiter is projected at several kilometers per second. It heads straight for the Earth until impact, forming a huge crater. The energy released was so intense that the rock of the Earth's crust liquefied. In less than a second, all the water within a 60-kilometer radius of the impact turns to steam. Animals in the vicinity are instantly killed. A few seconds after impact, the shock wave releases an unbearable heat that crosses the ocean. Everything in its path evaporates or melts. It would take just a few years for life to reappear in the impact crater, but over 30,000 years for a thriving ecosystem to develop. Scientific research has revealed the presence of burrows dug by shrimps and worms, as well as microfossils of plankton and algae. This suggests that the crater became habitable shortly after impact, even though the mass extinction was not yet over. Evidence of this impact was confirmed just before the 1980s. A thin black layer of clay just a few millimeters thick was revealed in some of the geological layers between the Cretaceous and Tertiary strata. This geological boundary contains abnormal levels of iridium. Although rare on Earth, iridium is found in abundance in certain meteorites. Scientists sometimes find minute quantities of iridium in terrestrial sedimentary rocks due to the fine, micrometeorite showers that are frequent on the planet. But analysis of this Cretaceous-Tertiary layer reveals far more. This is why it has been suggested that the planet must have suffered the fall of a huge meteorite. At the time, the crater could not be found. In 1981, two geophysicists employed by the Mexican oil company Petróleos Mexicanos investigated the Yucatan and discovered this unusual geological structure. The fall of this meteorite marked the end of the Cretaceous period and was responsible for a climatic upheaval that led to the extinction of non-avian dinosaurs and a large proportion of the animal and plant species at the time, both on land and in the seas. Without this event, Earth's history would be totally different, and we certainly wouldn't be here to talk about it. The Vredefort Dome is the largest known impact crater on Earth. It is located in South Africa, in the territory of the Free State Province. In 2005, Vredefort Dome was inscribed on UNESCO's World Heritage List for its scientific and scenic interest. The town of Vredefort was built inside the impact crater. The asteroid's impact dates back 2 billion years. Until recently, it was the oldest known impact crater on Earth, until the discovery of Manliksok crater in Greenland, estimated to be 3 billion years old. The asteroid's diameter has been estimated at 15 kilometers or 9 miles. It left a crater with a diameter of around 300 kilometers or 186 miles. Vredefort is one of the few craters to feature multiple terrestrial rings, a phenomenon often destroyed by erosion and plate tectonics. The dome is only the central part of the astrobleme, which actually extends over 360 kilometers or 224 miles in length, from Johannesburg to Welcome in the Free State. South Africa's geological stability has ensured the crater's continued existence. It is one of the only craters to have been crossed by a river, the Vaal, for almost 280 million years. The asteroid's impact would have really damaged the planet, causing fires all over the world. The enormous quantity of dust thrown into the atmosphere would have altered the climate for years. Located in Ontario, Canada, the Sudbury Basin is a crater formed some 1.85 billion years ago. It is the second largest known impact crater on Earth, but also one of the oldest. It is located on the Canadian Shield in the city of Greater Sudbury. The Sudbury Basin is 62 kilometers or 39 miles long, 30 kilometers or 19 miles wide, and 15 kilometers or 9 miles deep. The diameter of the meteorite has been estimated at around 10 kilometers. Some of the rock fragments ejected on impact traveled more than 800 kilometers or 500 miles and were scattered over an area of 1.6 million square kilometers. Scientists even suggest that such an impact may have scattered debris around the world, but that it has since been eroded away. The impact that created the Manliksok crater is thought to have occurred around 3 billion years ago. It is the oldest known terrestrial meteorite crater, yet remains totally invisible today due to erosion. By analyzing the nature of the rocks, scientists were able to prove that it was an asteroid impact. The asteroid would have had a diameter of around 30 kilometers or 19 miles and would have hollowed out a crater, originally 600 kilometers or 370 miles in diameter. At the time, only bacteria were beginning to populate the planet, but if such an object hit us today, it would exterminate all forms of life on Earth. Also known today as Meteor Crater, Barringer Crater is located in Arizona, USA, 60 kilometers or 37 miles east of Flagstaff. It is a well-preserved crater, formed by the impact of a small asteroid around 50,000 years ago. At the end of the Pleistocene, an object of peculiar composition hurtled towards the Earth. Made of iron and nickel, it is more likely to be a fragment of a planet core in the process of forming than a small body from the early solar system. As a result, it is much more resistant to the stresses imposed by the Earth's atmosphere than blocks of rock or ice. Once it reaches an altitude of around 14 kilometers or 9 miles, it eventually breaks up under the effect of increasingly dense layers of air. The meteorite splits into two parts, with a block of half its initial mass on one side and smaller fragments surrounding the initial impact over a diameter of 200 meters or 660 feet on the other. The main block, weighing 300,000 tons, hits the Earth at a phenomenal speed at 12 kilometers per second, or 7 miles per second. The collision forms a crater over a kilometer in diameter. At the time, this area was grassy savanna, occupied by mammoths and sloths. The impact releases energy equivalent to that of a thermonuclear explosion. All life is destroyed within a radius of several kilometers due to the blast and heat generated by the collision. The impact did not cause any noticeable change in the planet's climate. Meteor crater is bowl-shaped, measuring almost 1,400 meters or 4,500 feet in diameter, and 190 meters or 620 feet deep. Today, it is a popular tourist attraction. Warburton crater is located in Australia near the town of Ora Banda. Its diameter is around 5 kilometers or 3 miles. The asteroid's impact is thought to have taken place 100 million years ago during the Cretaceous, well before the impact that formed the famous Chicxulub crater. The Warburton crater was discovered in a very flat landscape. Erosion has taken its toll, and there's no sign of a crater on the surface. The impacting asteroid must have been between 100 and 200 meters in size, or between 330 and 660 feet in diameter. The crater is buried under several kilometers of sediment. It is not a single impact crater, but two craters, 200 kilometers or 125 miles wide, forming a structure 400 kilometers or 250 miles in diameter. The two impacts may have occurred simultaneously due to the fragmentation of an asteroid. The Populated crater is located in Siberia. It is the fourth largest known terrestrial impact crater, with a diameter of around 100 kilometers. It was formed by a meteorite impact 35.7 million years ago, during the Upper Eocene. It has been designated a geopark by UNESCO as a site with a specific geological heritage. Populated is also the world's largest diamond mine. During the Cold War, it was kept secret for decades. Shock waves from the impact would have instantly transformed graphite into diamonds within a radius of 14 kilometers or 9 miles. This mine would contain the equivalent of 10,000 billion carats. Just over 200 million years ago, an asteroid hit the north shore of Quebec in Canada, forming the Manicouagan crater. It is one of the oldest and largest impact craters on the planet. Due to erosion caused by glaciers, it is not easily visible on the Earth's surface. Its concentric structure, around 100 kilometers or 62 miles in diameter, is explained by the shock waves transmitted during the impact. The meteorite responsible measured around 5 kilometers or 3 miles in diameter. Comet Shoemaker-Levy, sometimes abbreviated SL9, is famous in astronomy for being the first to offer direct observation of a collision between two solar system objects outside the Earth. It has been closely observed by astronomers from all over the world. Comet Shoemaker-Levy broke up as it approached the planet Jupiter, colliding with it in July 1994. This collision led to the discovery of new elements about Jupiter and highlighted its key role in reducing the amount of space debris in the solar system. This comet is unusual in that it has been orbiting Jupiter for some time, rather than orbiting the Sun, like all the other comets known at the time. By 1992, it had already passed very close to Jupiter, just over 40,000 kilometers or 25,000 miles from the cloud tops. The 1994 collision was by far the closest and resulted in the comet's fragmentation. Each fragment is designated by a letter, ranging from fragment A to fragment W. The 1994 encounter was eagerly awaited. Astronomers had prepared their terrestrial telescopes, and several space observatories were ready to observe the impact live. On July 16, 1994, at just over 8 p.m., Fragment A struck the southern hemisphere of Jupiter at a speed of around 60 kilometers per second, or 37 miles per second. A fireball then formed. A fireball was formed reaching a temperature of around 24,000 degrees Celsius, or 43,000 degrees Fahrenheit, before dropping rapidly to around 1,500 degrees Celsius, or 2,700 degrees Fahrenheit. After this initial impact, observers see a huge black spot. These were the effects of impact debris. Over the following week, 21 impacts were recorded, the largest of which was produced by Fragment G. It took place on July 18th at around 7:30 a.m., creating a giant dark spot over 12,000 kilometers or 7,500 miles wide. On July 22nd, the final fragment, Fragment W, struck Jupiter. Direct observation of this collision provided a wealth of information about Jupiter. The planet has since been regarded as a kind of cosmic vacuum cleaner within the solar system. Jupiter's strong gravitational influence attracts numerous small comets and asteroids. Its impact rate is estimated to be between 2,000 and 8,000 times greater than that of our planet. In other words, if it weren't for Jupiter, asteroid impacts on the other planets in the solar system would be far greater. Astronomers have even gone so far as to hypothesize that without Jupiter to intercept potential impacts, collisions leading to mass extinctions, such as the cosmic impact that caused the Chicxulub crater, would be much more frequent, and Earth would certainly not have been able to witness the development of complex life forms. The study of past impacts, their frequency, and the reason why they occur allows us to better understand geological history. Collisions play an essential role in the formation of new galaxies, for example, and help us to understand these complex structures and their gravitational interaction. The study of impacts enables us to retrace the history of bodies and better understand the processes of accretion and planetary differentiation. Gravitational interactions between bodies during collisions can help scientists map the distribution of matter in the universe. Far beyond understanding the universe itself, the study of past cosmic collisions enables us to predict future events. In a much more distant future, around 4 billion years from now, our own Milky Way galaxy is predicted to collide with its nearest neighbor, the Andromeda galaxy. Scientists now determine that the two galaxies are heading towards each other at more than 100 kilometers per second. Even if the stars, because they are so far apart, pass each other without colliding head-on, the interstellar clouds will interact until they form a blaze of stars that exhausts almost all the available gas. This collision is considered a major encounter and will have a significant impact on the structure and evolution of both galaxies. Current research suggests that they will merge to form a new elliptical galaxy, devoid of interstellar gas. The latter will remain dominant in the local group. The first galaxies in the universe were far less massive than those we find today. According to current models, primitive galaxies gradually grew in size. How long a galaxy took to form is still unclear and depends on many factors. recent discoveries by the James Webb have revealed the formation of a very massive population of galaxies, produced between 500 and 700 million years after the Big Bang. One of these galaxies is thought to contain over 100 billion stars, as many as our own Milky Way galaxy. It took our own galaxy 13.8 billion years to form this many stars, while this young galaxy would have done the same in just 700 million years, i.e. 20 times faster. Today, there are two different scenarios to explain galaxy growth. On the one hand, there's talk of violent merging processes as large galaxies absorb smaller ones, and on the other, there's talk of a long continuous flow of gas being swallowed up by the galaxies. In both cases, many new stars are formed. It would seem that the latter theory played a significant role in the formation of galaxies in the young universe, and that the former theory of merging galaxies is what happened next. Galactic cannibalism is a relatively frequent phenomenon in the universe. It is a process whereby a massive galaxy attracts and devours a smaller galaxy until it is completely absorbed. This phenomenon played a key role in the evolution of our own galaxy, the Milky Way. Indeed, our own galaxy was built in part by devouring neighboring galaxies that sailed a little too close to it. Although this mode of assimilation may seem violent and brutal, it is widespread in the cosmic jungle. How are galaxies born and formed in the universe? And how does galactic cannibalism play out in practice? A galaxy is defined as a collection of stars, dust, and interstellar gas. Gravitation holds them together. Galaxies range in size from 2,000 to several million light-years across, and come in many different shapes. Thanks to the radiation they emit, galaxies can be categorized into normal and active galaxies. The latter have an active nucleus at their center, which is much brighter than normal. In the universe, when galaxies group together, we speak of clusters and superclusters. The galaxy to which we belong is the Milky Way. Today, tens of thousands of galaxies have been counted, and the observable universe is said to contain over 2,000 billion of them. Thanks to their studies and research, scientists have defined three main types of galaxy. The first are spiral galaxies like the Milky Way. These are the most numerous galaxies in the universe. They contain large quantities of gas and dust, as well as a disk containing young stars and a bulge containing old stars. This disk is often extended by one or two spiral arms and is filled with dust and gas stars. The second type of galaxy is elliptical. They are mainly made up of old stars and contain little gas and dust. Their structure is spheroidal. Finally, irregular galaxies, the last type of galaxy, are much less massive and contain young stars. From the very beginning of its formation, the universe must have been very uniform, devoid of stars, galaxies, or any other type of structure. Little by little, it was transformed into a spectacle of shapes and colors, filled with stars, galaxies, and galactic clusters. Originally, the density of the universe was only subject to small deviations from homogeneity due to the incessant movements of particles stirred up by radiation. Continuously created density perturbations use gravitation to expand. the force of attraction imposed by their own mass enabled them to draw in surrounding matter. This is how homogeneity gaps were created in the universe. Hypotheses concerning the formation of galaxies are based on two scenarios. On the one hand, the hierarchical theory implies that the first structures to form were those with a mass equivalent to around 1 million times the mass of the Sun. More massive structures, such as galaxies, were formed by the accumulation of smaller ones. Galaxies gathered in groups and clusters, culminating in imposing structures like superclusters linked by the force of gravity. Another theory, that of fragmentation, argues that the smallest structures originated from the fragmentation of the largest. In this sense, superclusters would have been created first. Then, yielding to the pressure of gas and radiation, they would have collapsed, occupying immense spaces and being subjected to the expansion of the universe. The large primordial structure would have flattened out under the forces of expansion, taking on the appearance of a sheet of dense matter. As it contracted, it would have given rise to filaments stretching over millions of light years, which would then have split into smaller entities that would have become galactic clusters and then simple galaxies. Current research favors the first theory. However, various data still cast doubt on this theory. Indeed, astrophysicists have observed that the most massive galaxies created their stars very early in the history of the universe. This remains a mystery. Several 100 million years after its formation, the structure of the first galaxies begins to take shape. They consist of globular clusters, the central supermassive black hole, and the galactic bulge containing stars. During this period, the galaxy is in the throes of star formation. Then, over the next 2 billion years, matter settles in the galactic disk. However, the galaxy will continue to absorb surrounding matter throughout its lifetime. The evolution of a galaxy can be strongly affected by interaction or collision events. Indeed, collisions are far from rare in the universe. Given the vast distances separating stars from one another, collisions are extremely rare. However, the dust and gas of the two structures mix and interact. The gravitational forces at play disrupt the original structure of each galaxy, forming zones of higher density. This leads to the formation of new stars. In the early history of the universe, galaxies were closer together and more likely to collide. Today, despite the expansion of the universe, galaxies are still showing signs of merging and colliding. Galactic cannibalism sometimes occurs when a massive galaxy collides with a smaller one. As a result, the former literally swallows the latter until it is completely absorbed. Intergalactic interactions occur when one galaxy is disrupted by the gravitational field of another. This can take the form of a minor interaction, as when a satellite galaxy disturbs the arms of a spiral galaxy, or a major interaction such as a collision or merger of two galaxies. Collisions occur when the two galaxies collide at a speed that allows each to continue on its course. Stars do not collide, but gas and dust do. The interstellar medium heats up, and galaxies can see their trajectories deviate. In most cases, their original shape is altered. Another, more violent interaction phenomenon is galaxy mergers. This occurs when two galaxies move towards each other, but neither can free itself from the other's grip. This has major consequences for their metabolisms. In most cases, the two merging galaxies form a single larger galaxy. When one of the two galaxies is much smaller than the other, the merger is akin to galactic cannibalism. The larger one remains unchanged, but dislocates the smaller one and devours it entirely. In the Lynx constellation, two galaxies were caught in the act of cannibalism. NGC 2798 is a barred spiral galaxy, 93.9 million light-years away. Its diameter is around 76,300 light-years. NGC 2799 is a Magellanic-type barred spiral galaxy. Its diameter is around 55,400 light-years. NGC 2798 was first discovered in 1788 by William Herschel due to its slightly higher brightness. NGC 2799 was discovered in 1874 by astronomer Ralph Copeland. Just a few years ago, spectacular images taken by the Hubble telescope immortalized a scene of cosmic cannibalism between these two distant galaxies. In the image, NGC 2798 appears like a vacuum cleaner, drawing the stars of NGC 2799 into its center. Although the space between the stars is so large that stellar collisions are unlikely, the sucked-in stars shine brightly and appear to be caught up in an uncontrollable chaos. The Milky Way, our galaxy, is part of a large group of galaxies known as the Local Group. Some 60 galaxies belong to this group. The Local Group itself belongs to a supercluster of galaxies known as the Local Supercluster. Within the local supercluster sit dozens of smaller galaxy clusters like the Local Group. The local supercluster is centered on a giant cluster of galaxies called the Virgo cluster. This cluster lies 50 million light-years from the Milky Way. Within the Virgo cluster lies a giant cannibal galaxy, Messier 87, which attracts and absorbs its neighboring galaxies. The Virgo cluster is a gigantic cluster located between 48.9 and 71.8 million light-years away. It was discovered by Charles Messier in 1781 when he drew up a map of the most important galaxies, including M87. The Virgo cluster is located in the constellation Virgo. It is thought to contain between 1,300 and 2,000 galaxies, most of them visible through a small telescope. It comprises a heterogeneous mix of spiral and elliptical galaxies. The Virgo cluster is an agglomeration of at least 3 very different subclusters. Virgo A is the one centered on the giant elliptical galaxy Messier 87. It is the dominant group of all the subclusters, composed of a mixture of mostly gas-poor, spiral, elliptical, and lenticular galaxies. Recent X-ray observations by the Chandra Space Telescope suggest that 3 subgroups have merged to form a single cluster. The other surrounding clouds and smaller galaxies are also moving closer to the cluster center. Even more distant galaxies and galaxy groups are finding themselves attracted by the Virgo cluster's gravity and will certainly merge with it in the future. These data imply that the Virgo cluster is relatively young and still forming. But now, back to the giant galaxy we're interested in the direction of Messier 87. Messier 87 is also known as NGC 4486. It is an elliptical supergiant galaxy. Some 50.2 million light-years away, it remains the largest and most luminous galaxy in the Virgo cluster. M87 was discovered by German astronomer Johann Gottfried Kohler in 1779. Charles Messier rediscovered it and included it in his catalog, published in 1781, in which M87 is listed as the 87th object. In the 1880s, Messier 87 was listed as NGC 4486 in a catalog of nebulosities and star clusters compiled by astronomer John Dreyer. In 1918, an American astronomer, Heber Daust Curtis, noted that Messier 87 had no spiral structure, but a curious straight ray, apparently connected to the nucleus by a thin line of matter. It was American astronomer Edwin Hubble who later classified Messier 87 as one of the brightest globular nebulae. In 1926, he created a new classification of nebulae. He included Messier 87 in the class of extragalactic elliptical nebulae with no apparent elongation. In 1956, Messier 87 was recognized as a circular, elliptical, EO-type galaxy. The Virgo A radio source was located in 1947 and confirmed as part of M87 6 years later. The source is the jet emanating from the nebula's core. Since its discovery, Messier 87 has been a favorite target for observation by amateur and professional astronomers alike, thanks to its proximity to Earth and its high luminosity in the sky. But what are its special characteristics? Messier 87 lies on a line joining the stars Epsilon, Virginis, and Beta Leonis near the constellation Bernice's Hare, at the northern limit of the constellation Virgo. The galaxy has an apparent magnitude of 9.59. A simple 6 centimeter or 2.4 inch diameter telescope can spot it, but its jet is difficult to observe without photographic aid, and will require a large diameter telescope and very good observing conditions. According to Hubble's classification, M87 is designated as an EOP galaxy. The EO designation implies an elliptical galaxy showing no flattening, and the P categorizes it as a peculiar galaxy as it does not fulfill all the characteristics of its class due to the presence of the jet emanating from its core. Messier 87 has a core surrounded by a diffuse, extended, dust-free envelope. M87's galactic halo and diameter are much larger than its visible part, reaching nearly 1 million light-years. M87's total mass is estimated at around 200 times that of the Milky Way. Its extended stellar envelope is around 978,000 light-years in diameter, compared with the Milky Way's 326,000 light-years. But how is M87 structured? The M87 galaxy features a supermassive black hole at its center. It has been named M87*, M87 because of its host galaxy, and the attribute asterisk in reference to the quasi-punctual source of radio waves. It is the first black hole to be imaged by Very Long Baseline Interferometry in April 2019. Its mass is one of the highest for this type of object, estimated at around 6.5 billion solar masses. The radius of its event horizon, the area around it in which no object or even a ray of light can escape the black hole's gravitational field, is 19 billion kilometers, or 11.8 billion miles, equivalent to 2.5 times the distance from the Sun to the Kuiper Belt. Its average density is equivalent to that of air at the level of Mount Everest. Surrounding the black hole is an accretion disk of ionized gas, oriented perpendicular to the jet. The gas is drawn into the black hole at a rate equivalent to about 1 solar mass every 10 years. At its maximum distance, the disk reaches a diameter of 24,800 astronomical units, or around 100 times the diameter of the black hole. The black hole appears to be rotating very rapidly. M87's black hole is offset by around 81.5 light-years from the galaxy's center, and is oriented in the opposite direction to the jet. Messier 87 has a stellar population dominated by old stars, which are population 2 stars containing few elements apart from hydrogen and helium. Little dust remains to form a diffuse nebula. The random orbital paths of Messier 87 stars stabilize the galaxy's elliptical shape. The space between each star is filled with an interstellar medium enriched with chemical elements ejected by the stars during their evolution. Throughout its evolution, Messier 87's interstellar medium has been continuously supplied with elements from Type 1a supernovae. Although Messier 87 is an elliptical galaxy and therefore does not have a dust band like spiral galaxies, optical filaments with a mass estimated at around 10,000 times solar mass have been observed within the galaxy. As a result, M87 is surrounded by a broad corona of hot, low-density gas. The galaxy has a high population of globular clusters. Indeed, one study estimated the number to be around 12,000, while the Milky Way only counts between 150 and 200. These clusters get larger the further away you are from the galaxy's center. Recent studies have revealed that Messier 87 has completely absorbed a galaxy over the last few billion years. Stars from a feast galaxy would have amalgamated with their fellow stars within the cannibal galaxy M87. Scientists were able to confirm this hypothesis thanks to an extended portion of Messier 87's outer halo, which appears much brighter than it would have if the merger had not taken place. The study focused on planetary nebulae, the envelopes of gas surrounding older stars, and not on the totality of stars, which are far too luminous and numerous to be studied individually. The motion of 300 planetary nebulae have been measured at distances close to those of M87. They look like little green lights from Earth, indicating their position and the speed of their movements. To better understand the research, compare it with water contained in a glass and poured into a lake. Even if it becomes imperceptible, it nonetheless generates disturbances that are likely to be visible. This is how the movements of planetary nebulae provide information about past fusion. The study revealed that a medium-sized galaxy is falling towards the center of Messier 87. Gravitational forces are such that stars are now spread over an area 100 times larger than the original galaxy. The stars coming from the Feast galaxy are stretched on all sides, causing the peripheral areas of the host galaxy to become brighter. Thanks to the merger, the Messier 87 galaxy has been enriched with younger, bluer stars. Within the constellation Furnace, some 70 million light-years from Earth, lies a vast lenticular galaxy with a disk but no well-defined spiral arms, known as NGC 1316, or Furnace A, or Fornax A. It was discovered by Scottish astronomer James Dunlop in 1826. The galaxy is described as a radio galaxy, since most of its energy comes from a jet emitting radio waves. Its nucleus has an emission spectrum with broad lines of weakly ionized atoms. NGC 1316 has had an eventful history, which was revealed when astronomers took a long look at it and its neighbor NGC 1317 using a 2.2-meter or 7-foot telescope at La Silla in Chile in 2010. While NGC 1317 appears to be a small spiral galaxy with a peaceful existence, NGC 1316 turns out to have swallowed up several other galaxies during its existence. The remains of this cannibalism are still visible. Astronomers have spotted unusual traces of dust within an envelope of stars, as well as smaller-than-average globular clusters. The first clue proves that NGC 1316 swallowed up a dust-laden spiral galaxy around 3 billion years ago. Galactic tidal effects have been spotted at the edge of NGC 1316. These are the remnants of stars torn from their birthplace and hurled into intergalactic space. Their gravitational effects on stellar orbits occur whenever a nearby galaxy approaches. The NGC 1316 galaxy has thus fed off other galaxies, and its environment is still disrupted as a result. It is now the most important source of radio waves in the Furnace constellation, and the fourth most important radio source in the universe. This is because matter is falling into a supermassive black hole at the galaxy's center. This same black hole has been fed by the galaxy's interactions with other galaxies. The black hole's mass is estimated at between 130 and 150 million times the mass of the Sun. NGC 1316 began its meal 3 billion years ago and is still in the process of digestion. Total fusion is currently in progress. Some scientists agree that it will eventually become a system dominated by a large galactic bulge. Although 3C297 can be seen completely alone, some 9.2 billion light-years from our planet, it was once part of a cluster of galaxies. Under the effect of its powerful gravitational force, its neighbors would have been drawn to it and then totally assimilated. According to the study carried out by the scientists, certain traces of a galaxy cluster have been found. Firstly, large quantities of gas were measured, with extreme temperatures of several million degrees. Then, a supermassive black hole swallowing gas and emitting a plasma jet over a distance of 140,000 light-years is also present. With these elements, the team expected to find a galaxy cluster, but in the end, almost all the galaxies are missing. They were certainly attracted and absorbed by the cannibal galaxy. The galaxy 3C297 is now cataloged as a fossil group. This is a galactic system in which some or all of the component galaxies have merged to form a single galaxy. 3C297 is even the most distant fossil group of galaxies ever identified. It will thus continue its solitary life for several billion years. NGC 7252, also known as Atoms for Peace, is a lenticular galaxy found in the constellation Aquarius, some 220 million light-years from Earth. The galaxy was discovered in 1785 by the astronomer William Herschel. NGC 7252 is the result of the merger of two galaxies. Around 1 billion years ago, two spiral galaxies collided, one becoming a host galaxy and the other a feast galaxy. Now, at the center of NGC 7252, lies a spiral-shaped disk, some 10,000 light-years across, undergoing an intense wave of star formation. It would appear that the two bulges of the original galaxies have merged, and that in the distant future, NGC 7252 will become an elliptical galaxy. The tidal tails that form as a result of the collision stretch for almost 500,000 light-years. The collision has given rise to young globular clusters and groups of bluish stars. Also known as Centaurus A, NGC 5128 lies in the constellation Centaurus, some 38.6 million light-years from Earth. This lenticular galaxy was discovered by astronomer James Dunlop in 1826 and is now the fifth brightest galaxy in the sky. It is one of the closest radio galaxies to Earth. Its active galactic nucleus has been the object of study by amateur and professional astronomers for many years. Seen from Earth, Centaurus A is a galaxy with an extraordinary morphology. It resembles a lenticular or elliptical galaxy with a superimposed band of dust. It is this particular morphology that has led to the explanation that it is the result of a merger between two smaller galaxies. NGC 5128 contains an active core due to the presence of a supermassive black hole, from which two opposing jets of matter flow. Old red stars populate the central zone. The central zone is crossed by a curved disk of dust containing atomic and molecular gases. New stars are born near and inside the disk. The mass of Centaurus A's supermassive black hole is estimated at 55 million solar masses. Research has not yet determined whether this black hole has always been within Centaurus A, or whether it is the result of a merger with a spiral galaxy. The galaxy's core is very compact and shows a variation in the intensity of its radio and X-ray radiation. Linear jets shoot out from either side of the nucleus, expanding into mushroom-shaped jets when they reach a distance of 16,300 light-years. The dust band crossing NGC 5128 is a disk seen from the side, 26,100 light-years in diameter, and 652 light-years thick. It is made up of metal-rich stars, nebulae, and dust clouds. Within the dust belt, a burst of star formation began 50 million years ago. The rate of star formation appears to be 10 times higher than in the Milky Way. Centaurus A produces a lot of energy from gas falling back into the central black hole. Some of it is then propelled back into the two jets at impressive speeds. The northern jet is clearly visible, while the opposite southern jet is much less visible, and has only been discovered thanks to a few knots. These jets are linear in shape until they reach the interface of the galaxy's interstellar and intergalactic gas, where a shock wave forms and they take on the shape of mushrooms. Their total length is around 30,000 light-years. Thanks to a technique using near-infrared images taken with ESO's 3.58 meter or 12-foot diameter New Technology telescope, astronomers were able to observe Centaurus A swallowing its meal with flawless precision. The little spiral galaxy appeared twisted and distorted. Thousands of star clusters swirled inside Centaurus A, representing the crumbs of cosmic fusion. To witness the meal of a giant cannibal galaxy live in this way remains rare and exceptional. The constellation Pegasus dominates autumn nights. It can be spotted in association with Perseus, Andromeda, and Cassiopeia. These are all neighboring constellations. Pegasus forms a majestic square of stars, the main part of the constellation. Within this constellation, Edward Stephan first spotted a group of galaxies in 1878. At the time, it was catalogued as an aggregate of nebulae, but it was later revealed by Edwin Hubble in 1924 that these were galaxies made up of billions of stars, far removed from the Milky Way. With a magnitude of 14, a telescope of at least 20 centimeters or 8 inches in diameter is required, as well as good observing conditions to catch a glimpse of the quintet. Stephan's quintet is made up of 5 galaxies: NGC 7317, NGC 7318A, NGC 7318b, NGC 7319, and NGC 7320. The first 4 are located relatively close together, around 340 million light-years from the Milky Way. Their spiral arms and disks are highly altered by tidal forces. NGC 7320 is much closer to us, between 35 and 40 million light-years away. These 5 galaxies show clear signs of gravitational interaction. Filaments of gas and stars are escaping from them as a result of the attractive forces that bind them together. NGC 7318A and NGC 7318b show the strongest interaction. A large proportion of their components have intermingled, forming a zigzag structure from which it's easy to spot their 2 bright cores. In 2018, the galactic cannibalism of Stephan's quintet was observed in even greater detail. Indeed, thanks to the extreme image quality of the Canada-France-Hawaii telescope, new information has been uncovered about how the quintet formed. While the researchers were originally capturing images of NGC 7331, a nearby spiral galaxy, their attention was focused on a concentration of galaxies in its background. This concentration turned out to be Stephan's quintet. This revealed an extensive red halo of older stars, centered on one of the elliptical galaxies, NGC 7317. These data show that the quintet is still interacting strongly, whereas scientists previously thought the opposite. What's more, NGC 7317, thought to be rather quiet, turns out to be still very active with the other members of the group. Stephan's quintet is indeed the scene of widespread galactic cannibalism. It is a highly coveted object of study for astrophysicists wishing to investigate the collective evolution of galaxies undergoing interaction, collision, or shock processes. In the long term, this cannibalism should lead to the formation of a single giant elliptical galaxy. Within the Eridan constellation, a magnificent pair of galaxies clearly displays its interaction. They lie more than 50 million light-years from Earth. The first stretches over 300,000 light-years in diameter, and the second over 240,000 light-years. These are the NGC 1531-1532 pair. NGC 1531 is a small lenticular galaxy located 54.5 million light-years away. It was discovered by astronomer John Herschel in 1835. It has a high surface brightness and an estimated diameter of around 23,800 light-years. NGC 1532 is a very large barred spiral galaxy. It lies 47.3 million light-years away and was discovered in 1826 by astronomer James Dunlop. Its diameter is currently estimated at around 303,000 light-years. The larger of the two, spiral galaxy NGC 1532, has drawn dwarf galaxy NGC 1531 into its gravitational influence. The latter is now a prisoner, subject to the forces imposed on it by the larger galaxy. In the long term, it will disappear in a total merger with NGC 1532. Thanks to the 8-meter or 26-foot diameter Gemini South Telescope at Cerro Pachon, Chile, an exceptionally splendid image of the NGC 1531-1532 duo has been obtained. NGC 1532 is in the foreground, beset by bands of dust. NGC 1531 lies in the background, but is easy to spot thanks to its bright core just above the center. All along the upper right edge of the front spiral arm, numerous young clusters of bright blue stars appear, born of the gravitational attraction residing between the two galaxies. Messier 51 is the most easily observable pair of interacting galaxies. Simply by using binoculars with 10-time magnification, you can make out the two tiny spots next to each other. The two diffuse stars separate as soon as you use an 80mm telescope. With a 200mm telescope, the two galaxies can no longer hide their bright cores and quasi-stellar appearance. Finally, with a 400mm telescope, the main galaxy clearly displays its spiral arms, which are covered with small knots that are in fact large star clusters. Charles Messier first discovered this galaxy in 1773 in the constellation of the Hounds. It lies more than 30 million light-years from Earth. M51 is also known as the Whirlpool Galaxy. It is the result of the meeting of two galaxies. NGC 5194 is the larger of the two. It is a spiral galaxy. NGC 5195, the smaller of the two, is a lenticular galaxy. The larger galaxy tugs so hard at its smaller companion that the smaller galaxy is completely distorted, making it difficult for astronomers to classify it. A bridge of matter appears to link the two objects, but this is in fact a deceptive perspective effect. Tiny NGC 5195 lies a few 100,000 light-years behind NGC 5194. Around 500 to 600 million years ago, NGC 5195 would have crossed the disk of the larger one. The smaller galaxy would have penetrated the disk from behind towards us, and even made another encounter between 50 and 100 million years ago to reach its current position. The interactions between these two galaxies produced a flurry of new stars. Using the Hubble telescope, astronomers have detected more than 100 ionized nebulae in the larger of the two. In the Sagittarius constellation, one particular galaxy is shaped like a bird. With the scientific names ISO 593, IG-008, but better known as Tinkerbell, this galaxy lies around 650 million light-years from Earth. Its wings extend over 100,000 light-years, roughly the size of our own Milky Way. This marvelous star is in fact the result of the encounter between two spiral galaxies and an irregular galaxy, although scientists have long thought that only two galaxies were involved in this collision. Thanks to ESO's Very Large Telescope, a team of astronomers has now been able to study this peculiar triple system in a little more detail. The images reveal two galaxies interpenetrating perpendicularly, forming the body and wings of the creature. The third massive irregular galaxy forms the bird's head. This is where stars are born at a spectacular rate of nearly 200 solar masses per year. It is the system's main source of infrared luminosity, despite being the smallest of the three galaxies. This trio of galaxies strongly resembles a winged creature. The result is a mega-galaxy called the Tinkerbell Triplet. Located in the constellation of the Sculptor, some 423 million light-years from us, lies the Cartwheel Galaxy, a lenticular ring galaxy, also known by its scientific name, ESO 350-40. With a diameter of around 180,000 light-years, it is a larger galaxy than the Milky Way. It was first observed by astrophysicist Fritz Zwicky in 1941. Its name was given for obvious reasons. Its shape resembles that of a wheel, with a hub in the middle, the rim around the rim, and the semblance of spokes running from the center to the periphery. This particular shape is thought to be the result of a collision with a small galaxy around 200 million years ago. Prior to the impact, the Wagon Wheel Galaxy would have had a spiral shape, like that of the Milky Way. The small galaxy would have passed through it, creating a shock wave and a gigantic gravitational disturbance. As the Wagon Wheel Galaxy is of greater mass than the galaxy responsible for the impact, the latter will eventually be swallowed up by the larger one. Thanks to the James Webb Space Telescope, we were able to observe this galaxy in all its splendor, as well as the dust that surrounds it. The collision between the two galaxies has formed two rings extending from the center of the galaxy to its periphery. The first ring contains a lot of dust and gigantic clusters of young stars, making it very luminous at its core. The second ring has been extended for 440 million years. It collides with the surrounding gas, giving rise to hundreds of millions of new stars. A study of the galaxy reveals zones rich in hydrocarbons and other chemical compounds, as well as dust whose composition is very similar to that of terrestrial dust, composed of silicates. It is these zones that take on the spiral ray shape so representative of the wagon wheel galaxy. The Lyra constellation peaks at midnight in early July, passing close to the zenith at our latitudes. It revolves around its brightest star, Vega. NGC 6745 is a very special member of this constellation, 200 million light-years away. It is a pair of interacting galaxies. It consists of NGC 6745A, the main member, and NGC 6745b, its companion. A few 100 million years ago, the small irregular galaxy, NGC 6745b, would have partially passed through NGC 6745a. The latter was almost certainly a spiral galaxy before the collision took place. Its structure is now totally altered. This cannibal galaxy has absorbed most of NGC 6745b's interstellar medium, leaving the latter stripped of most of its interstellar gas and dust. Between the two galaxies lie star clusters around 10 million years old. This is gas extracted from the larger galaxy, which has begun to form new stars in large quantities. The constellation Bernice's Hare lies between Leo and Bouvier, with declinations between plus 13 degrees and plus 33 degrees. It can be seen from almost anywhere on planet Earth. Its brightest star is Beta, with a magnitude of 4.3. The Bernice Hare constellation is rich in galaxies and other telescopic objects. It also features a pair of galaxies in the throes of cannibalism. This is the Mouse Galaxy. NGC 4676A and NGC 4676b form a pair of lenticular galaxies. The pair was discovered by astronomer William Herschel in 1785. They were later listed in the index catalog as IC819 and IC820. The first member of this duo, IC819, is a vast lenticular galaxy. It is an active galaxy some 328 million light-years away. Its companion, IC820, is also a lenticular galaxy, 327 million light-years away. It is also referred to as a low-surface brightness galaxy, meaning that it is a diffuse galaxy whose surface brightness is less than 1 magnitude lower than that of the night sky. They are known as the Mouse Galaxies because of their long tidal tails of stars and gas. The pair are in the process of merging and will eventually form a single gigantic elliptical galaxy. The luminous star clusters, gas and stars currently present in the tails, will position themselves in the new galaxy or remain in orbit in its halo. In 2002, the Hubble Space Telescope captured an image through blue and orange filters, as well as through a near-infrared filter. This is the most precise image of the Mouse Galaxy available. Blue cascades in the IC820 galaxy reveal clusters of hot, massive young stars whose birth was triggered by gravitational perturbations when the two galaxies met. Matter flows between the two galaxies can also be observed. In the long tail of IC819 are clusters of young stars separated by brighter regions. This suggests that the star clusters were formed from the gravitational collapse of gas and dust that was originally in place within these zones. The blue then yellow color of the long tails contrasts with the brown of the galaxy core. Due to the gigantic size of the galaxies, the cannibalism process is proceeding very slowly, at an approximate radial velocity of 6,600 kilometers per second, or 4,100 miles per second. Full merger will take several hundred million years. In the Ophiuchus constellation lies NGC 6240, a vast irregular galaxy 352 million light-years from Earth. It was discovered in 1871 by French astronomer Édouard Stephan. NGC 6240 is characterized as a liner galaxy, meaning that its nucleus has an emission spectrum characterized by broad lines of weakly ionized atoms. NGC 6240 is one of the most powerful sources of infrared emission in the sky. They are in fact two galaxies in fusion, emitting gravitational jets of stars, gas, and dust. These ultra-bright infrared galaxies fascinate astronomers because of their powerful luminosity. They are generally the result of the merging of gas-rich galaxies, triggering a period of intense star formation. This, combined with the activity of their nuclei, is what gives them their high luminosity. NGC 6240 has two nuclei, corresponding to the final phase of the merger of the two galaxies. In the long term, only a single galaxy will remain. The supermassive black holes at the center of each galaxy will merge into a much larger black hole in a few tens or hundreds of millions of years. Today, however, they are separated by a distance of 3,000 light-years. Because of this proximity, astronomers believe that the two black holes have been spiraling around each other for 30 million years. Recently, thanks to the use of ESO's Very Large Telescope, details about the black holes have been spotted. In fact, not two but three supermassive black holes, tightly packed into a space no larger than 3,000 light-years, are in place at the heart of the galaxy. Such discoveries tend to confirm a hitherto hypothetical scenario of galaxy evolution. The process of two galaxies merging had already been envisaged, but these results show that several of them can merge at the same time, accelerating the process of forming very massive galaxies. NGC 2623 is a spiral galaxy in the constellation Cancer, some 279 million light-years away. It was discovered in 1885 by astronomer Édouard Stephan. This galaxy has many characteristics. First and foremost, it is a liner galaxy since its nucleus has an emission spectrum defined by broad lines of weakly ionized atoms. It is also luminous in the infrared and qualifies as a star-forming galaxy and an active galaxy. NGC 2623 has a very distinctive shape on the sky. This is due to a major collision and the cannibalism of a large galaxy on a smaller one. A breathtaking image taken by the Hubble Space Telescope has revealed a little more about this galaxy. The scene of cannibalism stretches over 100,000 light-years. Although the merging galaxy is much too far away for us to observe it live from Earth with the naked eye, Hubble has brought back some wonderful details. The two galaxies that now make up NGC 2623 were probably originally spiral galaxies similar to our own Milky Way. In the images brought back by Hubble, they appear to have collided. they were certainly each traveling on trajectories that brought them very close to each other. The gravity of the larger one disrupted that of the smaller one, bringing them closer together until the former literally devoured the latter. Now their orbits are distorted, their initial silhouettes have changed, and two long coils of matter can be seen, stretching over 50,000 light-years each. These are known as tidal tails and are being pulled apart at the start of each galaxy by the gravity of the other. As the collision took place obliquely rather than head-on, the tidal tails appear to be twisting somewhat. During the collision, huge clouds of gas collided, forming stars that can be seen in blue all around the tidal tails. They will only live for a few million years. At the heart of the colliding galaxies is total anarchy. Gas deprived of gravity forms arches and furious star formation takes place. The formation and death of stars leads to the creation of dust, which absorbs light and hides the view of what's going on behind it. In such encounters between two galaxies, the stars are, at this scale, so small that the chances of them colliding with each other are virtually nil. Clouds of gas, on the other hand, are much larger, which explains why they collide, resulting in the formation of new stars. Using techniques to date the stars involved in the collision, astronomers have estimated that the catastrophe occurred less than 100 million years ago, which is quite recent on the cosmic timescale. The chaos will calm down one day, and in a few million years, NGC 2623 will become a larger elliptical galaxy. The evolution of NGC 2623 reminds astronomers of the fate that awaits our galaxy. Within 4 billion years, the Milky Way will collide with one of our nearest neighbors, the Andromeda galaxy. The two galaxies are heading towards each other at a speed of approximately 430,000 kilometers per hour, or 270,000 miles per hour. The stellar halo of the Andromeda galaxy is much larger and more complex than that of the Milky Way. Andromeda is a notorious cannibal that has already swallowed up a good number of galaxies in our cosmic neighborhood. But more on that later. Astronomers have attempted to illustrate what will happen in this collision. As in all galaxy collisions, it would appear that the objects contained within, such as stars, will not collide head-on. Proxima Centauri, the closest star to the Sun, is almost 30 million times the diameter of the Sun. On a human scale, it's as if the Sun were roughly the size of a coin, and Proxima Centauri was 750 kilometers, or 460 miles away. On collision, the Andromeda galaxy will gradually annihilate the Milky Way, and the two will form a giant elliptical galaxy. Names have already been proposed for this new galaxy. One early suggestion is Milkomeda, a contraction of Milky Way and Andromeda. Some scientists, preferring to take into account the greater mass of the Andromeda galaxy, have proposed the name Andromilka. The fate of the solar system is a matter of conjecture. Scientists have estimated that it would have a 50% chance of being ejected 3 times further from the future heart of the newly merged galaxy than it is from the current heart of the Milky Way. In the event of the solar system being displaced towards the center of the collision, it would be disrupted by nearby supernovae. As a result, the main objects of the solar system would not suffer any significant damage. By then, however, the Earth will already have been a habitable planet for several billion years due to the Sun's increasing power. The Andromeda Galaxy, also known as Messier 31, is our biggest neighbor. With a magnitude of 3.4, it can be clearly seen by the naked eye in a dark sky as a diffuse elongated spot. It is all the more impressive when viewed through binoculars. Its luminous bulb is surrounded by a gigantic disk, the length of which is equivalent to 6 full moons placed end to end. With a 300mm telescope, you can see 2 dust bands and a few stellar concentrations. With a diameter of around 220,000 light-years, the Andromeda Galaxy is the largest in the sky, second only to the Magellanic Clouds. It is thought to contain some 1,000 billion stars, between 2 and 5 times as many as in the Milky Way. It lies around 2.5 million light-years from the Sun, in the Andromeda constellation. The first written mention of the Andromeda Galaxy dates back to 964, in Abd al-Rahman al-Sofi's book of Fixed Stars. It was then spotted by Simon Marius using a telescope in 1612, and photographed for the first time in 1887 by Isaac Roberts. The Andromeda Galaxy is the nearest spiral galaxy to the Milky Way, and is twice as large and more densely populated than the latter. It is sometimes even considered its twin. However, the Andromeda Galaxy appears to have formed 3 billion years ago, whereas the oldest star in our galaxy dates back over 13 billion years. Images of its core, taken with the Hubble Space Telescope, reveal 2 luminous structures. These have long been mistaken for 2 cores, but in reality, there is the true core, and alongside it a simple concentration of stars in close orbit. The Andromeda Galaxy is a coveted subject of study for astrophysicists. They seek to explain the physical characteristics of the galaxy's formation. It appears that the formation of the Andromeda Galaxy was the result of the collision of 2 galaxies. The first was present 7 billion years ago. A second, 4 times smaller, was brought into its path 4 billion years ago. The encounter resulted in cannibalism in favor of the larger one, giving rise to the Andromeda Galaxy between 1.8 and 3 billion years ago. This scenario also provides a better understanding of the composition of the halo of gas and stars that surrounds Andromeda. The latter is about 10 times the size of the galaxy itself, and is made up of diffuse clusters, shells, and giant star streams. The galaxy's cosmic cannibalism is now helping to explain its various components. The giant star streams and shells originate from the smallest galaxy, while the diffuse clusters and disk deformation originate from the largest galaxy. As the smaller galaxy is less massive, it forms fewer heavy elements and stars than the larger one. The Milky Way is the galaxy to which our planet Earth belongs. It is an immense disk of stars. It consists of an intensely bright, compact central region called the bulge, and less dense spiral arms. Our galaxy's disk is estimated to be 100,000 light-years across and 1,000 light-years thick. Since 1991, a team of astronomers has discovered that our galaxy is not a simple spiral, but a barred spiral galaxy, which implies that it has a short bar of stars on either side of the central bulge. It also turns out to have 4 spiral arms. From Earth, our view of the Milky Way is very different, as we observe it from the inside. It appears as a wispy band that encircles the entire sky. The Milky Way is made up of 200 to 400 billion stars, so far away that they are impossible to see with the naked eye. Barely 6,000 are visible without an observatory. Although they appear to be crowded together, on average several light years separate the stars from one another. Today, if there's one fact about the Milky Way that needs no further proof, it's that it's a cannibalistic galaxy. This gourmand has been feeding on its fellow creatures since the dawn of time, and is still in the middle of a meal. A team of scientists recently discovered the remains of a galaxy within the Milky Way. It is believed to be the remnant of a satellite that the Milky Way may have agglomerated early in its history. It has been christened Heracles, a name inspired by the Roman mythological hero Hercules, who plays an important role in one of the stories behind the Milky Way's name. The remains of the Heracles galaxy make up a third of the Milky Way's spherical halo. This encounter, which took place 10 billion years ago, was certainly a momentous event in the history of our galaxy. It's quite astonishing that the remains of Heracles weren't spotted earlier, given the important place they occupy in the Milky Way. But since the Milky Way had to be built from the inside out, it was necessary to study the central zones of the galactic halo, which are very difficult to assess, in order to better understand the mergers it underwent. For 10 years, data were collected through the Apache Point Observatory telescope in New Mexico. More than 500,000 stars in the Milky Way were studied through their chemical composition and velocity measurements. Scientists were thus able to determine which stars came from the Milky Way and which from the Heracles galaxy. Reconstructing the chronology of encounters between the Milky Way and other galaxies is crucial to understanding its current organization, which still bears the traces of this past cannibalism. However, the cannibalism of the Milky Way is not just a story of the past. The Milky Way, which appears as a calm milky band in the sky, is in fact a galaxy as violent as it is destructive. It draws in and swallows up all the smaller galaxies around it. Within the local group, galaxies are inevitably moving closer together. While collisions between stars are rare given the distance between them, clouds of gas are forced together until they compress and heat up. As a result, the largest galaxy devours the smallest. This is how the Milky Way attracts the small and large Magellanic Clouds. These are the two largest satellite galaxies in our neighborhood. The large cloud is around 160,000 light-years from the Sun, while the small cloud is 200,000 light-years away. It is estimated that there are around 3 billion stars in the small cloud, and 10 times that number in the big cloud. The latter is also home to one of the largest nebulae in the universe, the Tarantula Nebula. These two small dwarf galaxies find themselves drawn into the Milky Way by a bridge of matter, forming a ring around its poles. Little by little, the Milky Way snatches matter from these galaxies and brings it to itself. While the Magellanic Clouds were certainly once barred spiral galaxies, they now find themselves completely distorted by the gravitational pull of the Milky Way. And since the mass ratio is favorable to our galaxy, it should eventually annihilate the small and large Magellanic Clouds within its structure. In 1994, random images revealed an overdensity of stars close to the galactic center of the Milky Way. Being too massive to be a globular cluster, it found itself categorized as a Sagittarius dwarf galaxy, named after the constellation in which it lies. It lies 75,000 light-years from the Sun, and it turns out that the Milky Way is pulling this small galaxy towards it, so that its tidal arms are spreading out around the poles of our galaxy. Stars from the Sagittarius galaxy should quickly disperse and enrich the cannibal halo. Another galaxy appears on the Milky Way menu, the Great Dog Galaxy, known as Canis Major. This dwarf galaxy is located in the constellation of the Great Dog. It is currently the closest galaxy to the Milky Way, just 42,000 light-years from the galactic center and around 25,000 light-years from the solar system. It contains around 1 billion stars. The Big Dog Galaxy lies behind the plane of the Milky Way, in a region where stars and gas clouds are the densest, and consequently occulting. This is why it was only discovered in 2003, thanks to a large-scale infrared survey of the entire sky, carried out by a team of astronomers. The Great Dog Dwarf Galaxy is currently being totally dislocated by the tidal forces of the Milky Way. Its center is severely degraded, and a long filament of stars stretches out behind it in rings 3 times the circumference of our galaxy. Scientists estimate that within 2 to 3 billion years it will be completely digested by the Milky Way, and its stars incorporated into the structure of the cannibal. Curiosity about the night sky is one of the oldest in human history. It's easy to imagine early man marveling as much as we do at this bluish canvas cloaked in sparkling stars, and projecting his myths onto it. Today, astronomy and astrophysics are at the heart of our understanding of the physical world. Our knowledge of the universe is growing ever finer, even if in some respects it remains more mysterious than ever. The study of cannibalistic galaxies provides us with a dazzling sketch of large-scale cosmic evolution. These acts of cannibalism are very common among galaxies. Cannibalism is therefore far from being a barbaric act, but rather a natural process for galaxies. This phenomenon has a beneficial effect on stars, promoting their formation in the form of gigantic outbursts. Galactic collisions and mergers are fundamental processes that contribute to the formation and transformation of galaxies over time. Thanks to scientific advances and the development of observation tools that reveal minute details, we can now immerse ourselves in the heart of these cosmic interactions and learn more about how stars, gas, and other elements interact to give rise to new, more complex structures. Research into cannibal galaxies promises many more revelations. These phenomena are just one of the countless pieces of the cosmic puzzle still to be assembled. The universe may seem infinite to us, but let's not forget that our scale of the world is also infinite for the smallest elements that make up matter, namely subatomic particles. In fact, the human size is of the order of a meter. This is our reference point for observation. With sharp eyesight, it's possible to see several kilometers away, but also to notice details of the order of 1/10 of a millimeter. But with measuring equipment, we can go much further. far enough to deduce the existence of the primordial constituents of matter, the famous quarks. If you thought the atom was the smallest element in the universe, think again. Thanks to extensive research, notably at CERN's particle collider, we now know that every atom is made up of a nucleus and one or more electrons. Most atomic nuclei are made up of neutrons and protons, known as nucleons. Because of the negative electric charge of electrons and the positive electric charge of protons, these two elements are held together by the action of the electromagnetic force. This is one of the four great forces that govern the laws of physics as we know it. At the atomic scale, the most important forces are the electromagnetic force, the strong interaction that holds atomic nuclei together, and the weak interaction. The role of the latter is rather difficult to describe, yet still understandable to most people. But it is just as responsible for the radioactive decay of subatomic particles as it is for nuclear fusion at the heart of stars. The final fundamental interaction, and probably the best known of all, is the gravitational force. In other words, gravity. Its intensity depends, above all, on the mass of the objects in question. It is therefore very present on a cosmic scale, whereas its role at atomic levels is negligible. The atom is made up of neutrons, protons, and electrons. But is it possible to go even further? Not surprisingly, the answer is yes. At the heart of nucleons are other elementary building blocks of matter. These are the quarks. And when it comes to their size, things get even more complicated. But to understand better, we need to go back to the structure of the atom. The size of atoms varies according to the element considered, but the order of magnitude remains more or less the same, 10 to the minus 10 degree meters, or 0.1 nanometers. The atomic scale is therefore ridiculously small. An atom is not a ball of matter, contrary to what some simplified representations tell us. In fact, it's more like a ball of vacuum. After all, while the size of an atom is of the order of 10 to the minus 10th power meters, the size of its nucleus is 10 to the minus 15 power meters. The nucleus is therefore 100,000 times smaller than the atom itself. To help you visualize this difference, let's imagine that an atom is the size of a soccer field. How big do you think the nucleus would be in this representation? That of a player? A football? A red card? Well, no. The size of the core would be that of a marble placed in the center of the field. But then, if the nucleus is so small, why give atoms such dimensions? The reason is simple. Electrons must also be taken into account. In theory, electrons are elementary point particles. They have no size or dimensions. Almost all the mass of an atom is therefore concentrated in its nucleus. This is why we say that matter is essentially made up of vacuum. Of course, this is not visible on our scale. It's the forces acting between particles that give us the illusion that everything around us is full. So forget the idea of being able to pass through walls. We also know that electrons move in quantized orbits around the nucleus. Their probability of presence varies from place to place. So without experimental measurements, it's impossible to know the exact position of electrons around a given atomic nucleus using theoretical calculations. They are, probabilistic particles subject to the mysterious laws of quantum mechanics. Nevertheless, for each atom, we know the maximum distance of the electrons from the nucleus. And it's this maximum distance that sets the size of atoms at around 10 to the minus 10 power meters. Now back to the size of quarks. Just as electrons give atoms a certain diameter, quarks give protons and neutrons a diameter. And just like atoms, quarks are considered to be point-like particles. In this sense, quarks cannot have a size. However, if they were to have one, it would probably be less than 10 to the minus 18 power meters. That's 1,000 times smaller than a nucleon, itself 100,000 times smaller than an atom. Again, this order of magnitude is so minute that it's impossible for us to conceptualize. But if we make a comparison on our own scale, things become much more meaningful. So let's start by finding a substitute for our quark. To simplify things, let's take a 1-meter object. How about a baguette? Now we need to find something 1,000 times bigger to represent our nucleon. In other words, something a kilometer long. The Burj Khalifa, i.e. the world's tallest skyscraper, at some 828 meters high, would fit the bill perfectly. Well, we've got our quark, we've got our nucleon, now we need our atom. For that, we need something 100,000 kilometers long. Knowing that the Earth is about 12,700 kilometers, or 7,900 miles in diameter, we'll have to look further out, into the cosmos. Saturn, with a diameter of around 116,000 kilometers, or 72,000 miles, is the ideal candidate. So while the atom may seem infinitesimally small to us, it's actually a giant compared to the other components of matter. Just think, next to the atom, elementary particles such as quarks and electrons, if they had any size at all, would be no bigger than a baguette in front of Saturn. That's a bit of an oversimplification, but it does reflect the relative immensity of the world around us. Who knows? Perhaps our universe itself is just a drop of water in something much larger. Once this question has been posed, the answers are limited only by our imagination. Some may think of the multiverse, and others, the disturbing immensity of infinity. In the light of our current knowledge, there's nothing to suggest one hypothesis over another. While studies are underway to determine the nature of the observable universe, what lies beyond it remains a profound mystery. If indeed there is a beyond. We've seen the atom and its components. Let's consider this as a starting point for our fantastic epic journey towards the infinitely large. It's going to be a long road, so it's best to take it one step at a time. The question is what comes after the atom, and the most logical answer would be molecules. Indeed, a molecule is a structure, sometimes very simple, sometimes very complex, resulting from the bonding of several atoms. To avoid complicating things too much, we're interested in the water molecule. This is made up of 2 hydrogen atoms for 1 oxygen atom. Hence its name, H2O. Its size is in the nanometer range, or 10 to the minus 9 power meters. Again, it's tiny. In fact, it's estimated that a single drop of water is made up of around 3 times 10 to the 20th power water molecules. This quantity is simply mind-boggling. That's 300,000 million billion molecules. That's 300 billion times more than the number of stars in our galaxy. All in a droplet just a few millimeters in size. We can also assume that this drop of water must harbor some form of life. Single-celled organisms capable of growth and reproduction. The smallest of them measure just a few hundred nanometers. This is the bare minimum required to provide the genetic material necessary for the survival of these organisms. Human cells, on the other hand, are in the micrometer range. This means they are 1,000 times smaller than a millimeter, so you need an optical microscope to see them. This is also the norm for most bacteria, which are on average 2 micrometers long. In 2022, researchers at the University of the West Indies published their discovery of a giant bacterium in a mangrove sample. Called Thiomargarita magnifica, the individual cells of this titanic filament-shaped bacterium stretch up to 2 centimeters long. This has never been seen before, pushing back the limits of size among microorganisms. In fact, this bacterium would be visible to the naked eye, provided you pay close enough attention. For Olivier Gros, one of the researchers behind this discovery, it's a bit like observing a primate, the size of Mount Everest. So even on the scale of a single drop of water, the world is much larger than we can imagine. But our journey is far from over, and it's time for us to continue our ascent towards cosmic scales. Still taking a drop of water as our reference, we now need to move on to the size scales of our everyday lives. And what better way to do this than by the liter? To reach this quantity, we need no less than 20,000 droplets. But we can go even further by asking how many drops of water there are in all the oceans that cover the Earth. Several people have had fun doing the math, and the result they come up with is just incredible. Between 2 and 4 times 10 to the 25th power drops of water. That's around 100,000 times more than the number of water molecules in a drop. This puts things into perspective, doesn't it? We can do the same thought exercise, but this time comparing our own scale to that of our beautiful blue planet. To do this, we'll estimate that the average human height is 1.70 meters or 5.6 feet. In your opinion, if all the human beings currently living on Earth were to stretch out one after the other, how long could they grow? Would this human chain be big enough to go from one end of our planet to the other, passing through its center? Or even to equal the Earth-to-Moon distance? Well, if we estimate that there are currently 7.9 billion human beings on Earth, we get a length of around 13.4 million kilometers, or 8.3 million feet. That's well over the Earth's diameter, which is around 12,700 kilometers, or 7,900 miles. It's also far more than the Earth's circumference, around 40,000 kilometers, or 24,900 miles. But is it enough to cover the Earth-to-Moon distance? Well, yes. In fact, our natural satellite is not as far away as you might think. But we still have to travel some 400,000 kilometers, or 248,000 miles to reach it. However, our human chain would be far too short to reach the various planets in our solar system, starting with our nearest neighbor, Venus. Depending on the era, the distance between the Earth and its sister planet varies between 43 million kilometers, or 26 million miles, and 256 million kilometers, or 159 million miles. This is because the two planets have different periods of revolution around the Sun. Over the decades, they move towards and away from each other in a never-ending cycle. We've now entered the cosmos. Even if we stay within the solar system, which is only a tiny fraction of our galaxy, which itself is dust in the universe, the orders of magnitude are already beyond our comprehension. But that doesn't stop us from marveling at the most immense objects dotting the sidereal void. Let's start by looking around us to see which is the largest telluric planet. If the term doesn't ring a bell, we're talking about rocky planets composed essentially of rock and metal. Compared with gas giants, they are tiny, but their density is high. They are also characterized by the presence of water, in solid or liquid form, an element essential to the formation of life as we know it. In our solar system, there are 4 telluric planets. Classified according to their increasing distance from the Sun, they are Mercury, Venus, Earth, and Mars. Some may notice that Pluto is missing from the list, but this is no oversight. Indeed, due to its small size and haphazard orbit, Pluto, once considered the 9th planet in the solar system, was downgraded to dwarf planet status in August 2006, following a vote by the International Astronomical Union. That said, it remains one of the largest dwarf planets in the solar system, along with Eris, Ceres, Makemake, and Haumea, with a diameter of nearly 2,400 kilometers, or 1,490 miles. It is therefore 6 times smaller than the Earth, but that doesn't stop it from having its own satellites. The largest of these, Charon, is more than half the size of Pluto. It's as if our moon were the size of Mars. But back to our telluric planets. Which is the biggest? Is it Venus? Well, no. It's the Earth at the top of the podium. At the bottom is Mercury. Almost 3 times smaller and 20 times less massive than Earth, it's literally no match. Next comes Mars, which is almost 2 times smaller than our planet. In second place is Venus, with its rather inhospitable conditions. With atmospheric pressure 92 times higher than on Earth, heat of 462 degrees Celsius, or 863 degrees Fahrenheit, sulfuric acid rain, and winds of 400 kilometers per hour, or 250 miles per hour, the Shepherd's Star is not a good place to live. And yet, if its atmospheric composition had been different, Venus could have been an excellent candidate for a space colonization project. 1.16 times smaller than Earth, it also has a gravity very close to our own. We also know that water is present on Venus, but mainly in the form of vapor in its atmosphere. However, the presence of frozen water at depth cannot be ruled out. Unfortunately, given the distance separating us from Venus and the technical challenges posed by its atmosphere, colonizing Venus will probably remain a utopian dream forever. We now know that the Earth is the largest telluric planet in the solar system. But what's the biggest moon in it? To find out, we need to turn to the gas giants. Perhaps you're thinking of Titan? A colossal satellite almost as big as Mars orbiting Saturn. But Jupiter is home to the largest moon ever discovered. Its name, Ganymede. It crushes the 91 or so other moons of the gas giant. With a diameter of 5,268 kilometers, or 3,270 miles, 8% larger than the planet Mercury and 2% larger than Titan, it is the largest moon in the entire solar system. However, Its strange composition makes it rather less massive than the telluric planets. Ganymede is indeed the heaviest planetary satellite we know of, but its mass is equivalent to 45% of Mercury's, despite its larger dimensions. This is partly explained by the presence of an immense ocean beneath its frozen surface, which could contain more water than there is on Earth. Logically enough, if Ganymede is the king of the solar system's satellites, Jupiter, its home planet, is the queen. 11 times bigger than our blue planet and 318 times more massive, it's a veritable cosmic monster. In terms of volume, it could easily contain all the rocky planets and moons in the solar system. In fact, it would happily swallow up no less than 1,300 Earths. And with a diameter of over 140,000 kilometers, or 87,000 miles, it easily dwarfs all the other planets around it, including Saturn if we ignore its rings. Its atmosphere, churned up by gust storms and giant hurricanes, is mainly made up of hydrogen and helium, like the stars themselves. But at its heart, the great Jupiter is said to harbor a solid core. A ball of matter resembling the Earth, but 14 to 18 times more massive. This stony core would also be covered in ice and contain a metallic core, made of an alloy of iron and nickel. Jupiter is also home to the Great Red Spot, a vast oval-shaped storm of colossal size, enough to swallow the Earth 3 times over. Not to mention the violent winds that swirl around its surface, sometimes exceeding 1,400 kilometers per hour, or 870 miles per hour. By comparison, the strongest winds ever recorded on Earth were just over 400 kilometers per hour, or 250 miles per hour. Despite this blood-curdling description, Jupiter is far from being a threat to us. On the contrary, it plays a protective role, deflecting asteroids and comets that are on a potentially dangerous trajectory for the Earth. Some scientists even believe that the gas giant is one of the reasons why life was able to develop on Earth, without being totally wiped out by a series of cosmic collisions. There are many objects in the solar system that threaten us. Masses of rock and ice, drifting at breakneck speeds, waiting for the right opportunity to collide with us. Most of the asteroids we know are located either in the asteroid belt, behind the orbit of Mars, or in the Kuiper belt behind Neptune. But others are more devious, waiting in the shadows to cross our path one day. However, even if the Earth escapes the various threats of the cosmos, there is one that it will never be able to avoid. And paradoxically enough, it's this very threat that is the origin of life: the Sun. Both creator and destroyer, the Sun has been at the heart of many beliefs throughout human history. Its rays provide the energy needed to warm our atmosphere and enable photosynthesis in plants. Without it, we would never have seen the light of day, literally or figuratively. However, assuming we live another 5 billion years, we cannot escape the tragic end in store for our star. Today, what's known as a yellow dwarf, although ironically its volume is large enough to hold 1.3 million Earths. If our planet were 1.2 centimeters or 0.5 inches in diameter, the Sun would be 1.4 meters or over 13 feet in diameter. Even Jupiter, the largest planet in the solar system, is 10 times smaller by comparison. The Sun alone accounts for 99.86% of the solar system's total mass. And yet, our star is far from having reached its final size. At around 4.6 billion years old, it's estimated to be about halfway through its life. In its interior, nuclear fusion is taking place, resulting in a core temperature of around 15 million degrees Celsius, or 27 million degrees Fahrenheit. This fusion is the source of the sun's heat and radiation. But like everything else in this world, our sun is not eternal. The day will come when the sun will have exhausted all its fuel reserves. It will then begin a slow descent into hell, starting with its expansion into a red giant. At the heart of our star, hydrogen atoms fuse to form helium atoms. This high-energy reaction generates incredible pressure, which tends to expand the star. At the same time, the force of gravity acts to compress the sun. This balance guarantees the stability of our star. But little by little, the amount of helium in the core increases as the hydrogen is consumed. Eventually, the pressure exerted by fusion will decrease sufficiently to cause the core to contract. This will increase the temperature and pressure in the outer layers of the core. As a result, the hydrogen fusion zone will begin to extend beyond the core, towards the outer layers of the sun. Hydrogen outside the core will be hot and dense enough to undergo nuclear fusion. Our star will then begin its transformation into a red giant. As the fusion zone expands, the core will continue to contract, while the outer layers of the sun will begin to expand. Our star will begin to inflate like a balloon. It will first engulf Mercury, then Venus, but the fate of the Earth is less certain. Our planet lies on the edge of the zone where the sun is set to expand, becoming a red giant. As the sun expands, its radiation will increase considerably. Its surface will be hotter than before, resulting in increased luminosity. Eventually, the sun will shed its outer layers into space, in the form of solar winds and jets of matter. These expelled layers will form an envelope of gas and dust around the core, creating a planetary nebula. This marks the end of the red giant phase. All that will remain is a dense hot core called a white dwarf, the only vestige of a star that was once resplendent. This white dwarf will be composed mainly of helium and carbon. It will no longer burn fuel, but will continue to glow for a while, emitting residual heat. Then it too will gradually cool down. It will cease to glow and become a dark relic in the darkness of space. In a way, this ending is melancholy sweetness. All the more so when you consider the fate of supermassive stars, which die in a tremendous cosmic explosion called a supernova. All stars and celestial bodies, no matter how immense, will one day come to an end. So before they disappear forever into the sidereal void, let's take advantage of the fact that they are still visible to set off on a voyage of discovery. After starting out in the infinitely small and arriving at the limits of our solar system, it's time for us to go further, much further. Get ready, because we're about to continue our journey into the immensity of our entire universe. Together, we're going to discover the most gigantic objects in the cosmos. In our solar system, we know that Jupiter is the largest of all the planets. Yet across the vastness of our universe and the trillions of billions of galaxies it harbors, there are bound to be stars orbiting a star whose size would make our local giant look like a dwarf planet. Exoplanets so massive, they could be compared to small stars. Well, at the risk of disappointing you, it's unlikely that such planets exist. for the simple reason that too much matter collapses gravitationally, generating sufficient temperature and pressure to trigger nuclear fusion. As a result, what could have become a giant planet often becomes a star. As a result, the largest exoplanets ever discovered are similar in size to Jupiter, although they may be more massive. Such is the case of Kepler 1647b, an exoplanet detected by NASA's Kepler Space Telescope and located nearly 3,700 light-years from us. Its discovery was announced in June 2016, and since then, it has been heralded as the largest exoplanet ever discovered. Its mass and diameter are said to be similar to those of Jupiter. However, Kepler 1647b has an interesting feature. It is a circumbinary exoplanet. This means it orbits two stars comparable to our own Sun. This particular arrangement of stars is reminiscent of the famous sand planet Tatooine from the Star Wars saga. According to the astronomers' observations, Kepler 1647b takes around 3 years to orbit this binary system. This is an interesting discovery, as it places the giant in the system's habitable zone. In other words, it orbits at a distance where the appearance of liquid water is likely. However, Kepler 1647b is a gas planet. It is therefore unlikely to harbor life as we know it. On the other hand, like Jupiter or Saturn, it could have rocky moons, which could then offer much more favorable conditions. Now, if you point a pair of binoculars at the constellation Centauri, you'll be able to spot a young star comparable to the Sun. Located just 310 light-years from Earth, it's called HD 114082. We're not interested in this star, however, but in the exoplanet orbiting it. Named HD 114082b after its star, it is another gas giant. The surprising thing about this star is that its radius is similar to that of our beloved Jupiter. Yet its mass is 8 times greater, some 2,500 times the mass of the Earth. Simply gigantic. Another surprising fact about this super Jupiter, as astronomers call it, is that it orbits very close to its star, about half the distance to the Sun. As a result, its period of revolution is just 110 days. By comparison, Jupiter takes 12 years to orbit the Sun, and Neptune, the most distant gas giant in our solar system, takes 165 years to make a complete revolution. HD 114082b is also the youngest known gas giant whose radius and mass have been determined. But something's not quite right. Based on current models that determine the maximum size and mass that planets can have, our super Jupiter is around 2 to 3 times too dense for such a young gas giant. How can this anomaly be explained? There are several hypotheses. First, it could be that an error was made in the measurements. But with this kind of discovery, the data is always checked several times. Another possibility is that the models used by the astronomers are incorrect. Finally, it's possible that HD 114082b is an anomaly, a kind of cosmic scale error of nature, with an unusually large solid core, which would explain its incredible density. For the moment, the question remains unanswered, and we'll have to wait for further discoveries before we have a definitive answer to this enigma. Speaking of cosmic anomalies, we can also mention the case of AB Aurigae b, also known as ABRB. This is a gas giant exoplanet with a mass 9 times that that of Jupiter. This makes it the most massive exoplanet ever discovered. It lies some 508 light-years from Earth. What makes it so spectacular is not just its extraordinary mass. Rather, it's the fact that it's the first directly observed exoplanet still embedded in the disk of gas and dust from which planets are formed. This is known as the protoplanetary disk. To explain the birth of stars, researchers put forward two hypotheses. The first is called core accretion. The material making up the disk condenses by accretion until it forms a solid core, essentially made up of rocky materials and metals. Once this core has reached critical mass, it in turn accretes gases, mainly hydrogen and helium, until it forms a gas giant planet. The second hypothesis is that of disk instability. This involves the collapse of parts of the protoplanetary disk under the effect of gravitation. This collapse condenses the material to form a gas-only planet with no rocky core. Given the vast distance separating ABRB from its star, almost 93 times the distance from the Earth to the Sun, astronomers are leaning towards the disk instability model to explain its formation. The shape of the spiral arms of the protoplanetary disks surrounding the star also supports this hypothesis. Having a direct image of ABRB's formation around its star is therefore proof that gas giants can form through disk instability. At least it's an observation that calls into question standard models of planet formation. This is because until now, the vast majority of exoplanets observed had orbits around their stars that did not exceed the distance between the Sun and Neptune. However, ABRB orbits 3 times further than Neptune from the Sun. Unfortunately, it's still too early to say anything about this strange giant planet. In fact, it's only at the beginning of its formation process, rather like a fetus in gestation. It is even approaching the maximum size to be classified as a planet, rather than a brown dwarf. In other words, an aborted star too small to trigger a stable hydrogen fusion process. These stars are halfway between stars and planets, condemned never to shine. Be that as it may, the discovery of ABRB is just further proof of just how complex the mechanisms governing our universe really are. New astronomical observations continually challenge our current theories, improving our understanding of the universe. Planet formation is highly complex and messy, and there are still many surprises in store for us. And we're going to continue our discovery of those surprises. This time, we're going to focus on the telluric planets, i.e. the rocky planets. Just as there are super Jupiters, there are also super Earths, which make our blue planet look like a small moon. One of the most famous of these is HD 219134b. When its discovery was announced on July 30th, 2015, it was the closest telluric exoplanet to Earth ever discovered, just 21 light-years away. But today, that title goes to Proxima Centauri b, which is 4.2 light-years away. That said, HD 219134b is still quite close, and assuming we could ever travel at the speed of light, getting there would not be impossible. However, it's not in its star's habitable zone, so an expedition there seems a bit pointless. All the more so as its surface temperature exceeds 400 degrees Celsius, a veritable furnace. But the reason why HD 219134b is of such interest to scientists is that its proximity allows for a more in-depth study of neighboring telluric planets outside our solar system. Similar to our own planet, in terms of composition and density, Super-Earth HD 219134b differs above all in its radius and mass. These two parameters are respectively 1.6 and 4.5 times greater than those of the Earth. This may sound huge, but it's nothing compared to the planet that is still considered the most enormous of all rocky planets ever discovered. Its name? Kepler 10c. This exoplanet was detected by NASA's Kepler Space Telescope in 2011. It lies around 560 light-years from Earth in the constellation Dragon. Until then, the telluric planets discovered had masses equivalent to 10 times that of Earth for the largest, but the discovery of Kepler 10c has put things into perspective. This mega-Earth is 17 times more massive than our planet, with a radius 2 times greater. Yet it has the same density. Before its discovery, theorists believed that such planets could not exist. Their argument was that beyond a certain mass, the solid body must capture the surrounding gases, as well as those it produces, to gradually metamorphose into a gas giant. However, this is not the case with Kepler 10c, which remains an enigma for science. In fact, early observations of this star only hinted at its size, so astronomers thought it must be a Neptune-like planet. The surprise came when Kepler 10c's mass was finally measured. Another troubling fact about this star concerns its age. The giant planet is thought to be around 10 billion years old. At that time, the first generation of stars had only just completed their life cycle, and the heavy elements needed to form rocky planets were not very abundant in the universe. Proof that there are certainly worlds similar to our own, but much older in the cosmos. Worlds that could potentially have been home to life for billions of years, giving organisms time to evolve and perhaps even travel to other planets. Although this is purely speculative, it does give us confidence that we may one day encounter other intelligent life forms. Among the bestiary of ultramassive telluric planets, TOI 849b by its scientific name. On NASA's official website, it's presented as a gas giant, yet there's hardly a gaseous envelope to be found on this planet. Only a solid body 3.5 times larger than the Earth, and 40 times more massive. TOI 849b is about the same size as Neptune, but outweighs it by 2.3 times in terms of mass. It is one of the densest planets of its size ever observed. But in reality, TOI 849b doesn't deserve the title of super-Earth, since it is in fact the residual core of a gas giant. TOI 849b could be a reflection of Saturn or Jupiter, should they lose their gas envelope. This hypothesis seems highly likely, given that TOI 849b orbits so close to its star that it circles it in less than a day. It therefore receives 2,000 times more radiation than we do from the Sun. Its gaseous layers may well have been swept away by its star. If this scenario is correct, TOI 849b would be the largest known gas giant core. However, one question remains. If TOI 849b's gas envelope was indeed blown away by its star, how come there's still a residual part of it? Only more detailed observations will one day be able to solve this planetary mystery. Perhaps even telescopes will one day point their sensors at even more monstrous planets, putting astrophysicist models to an even greater test. In any case, if we want to see in detail what the largest objects in the universe are, we can't limit ourselves to planets. We need to go one step further, one step higher, to the stars. Earlier, we saw that within the solar system, nothing compares to the Sun's 1.4 million kilometer diameter. And yet, as imposing as it is in comparison to us, it's just a speck of dust compared to the biggest star we know. Until recently, this record was held by VY Canis Majoris, a red supergiant star in our galaxy 5,000 light-years away. To our eyes, its size seems infinite. 2 billion kilometers in diameter, or around 13 times the distance from the Earth to the Sun. If VY Canis Majoris stood in the place of our Sun, it would be large enough to engulf our solar system all the way to Jupiter. Its size is therefore around 1,500 times that of our star, which in comparison would be no bigger than a football against the Eiffel Tower. But the biggest star we know today is not VY Canis Majoris, but UY Scuti, another red supergiant located in the Sobieski Shield constellation, 9,500 light-years away. 1,700 times larger than the Sun, it could extend as far as Saturn if placed at the center of the solar system. However, when we talk about giant stars, we also need to consider their mass. Indeed, while UY Scuti is the largest of them all, the title of the most massive known star goes to R136A1. It weighs around 250 solar masses, whereas astrophysicists' limits for stars are more like 150 solar masses. What's more, R136A1 is also one of the brightest stars in the cosmos, shining as brightly as 10 million suns combined. Located within the Tarantula Nebula in the Large Magellanic Cloud, a dwarf galaxy close to the Milky Way, its position makes it difficult to observe. In fact, the star is part of the R136 supercluster of stars, 9 of which have a mass more than 100 times that of the Sun. Researchers had to make several measurements and observations to correctly identify all the stars in the R136A group, itself part of the R136 star cluster. Interestingly, R136A1 is located in the Tarantula Nebula, which, as well as being spectacular, is also the largest we know of. It extends over a vast region of space covering some 1,000 light-years. That's around 9.5 million billion kilometers. It's so large that it's even visible to the naked eye from the southern hemisphere. It's even a popular target for amateur astronomers. The Tarantula Nebula is also a cosmic wonder, offering fertile ground for astronomers studying star formation and death. In 1987, a brilliant supernova occurred within the nebula, enabling astronomers to study this prodigious cosmic phenomenon at close quarters. Also in the nebula family is the Orion Nebula. Visible to the naked eye as a blur in the sky near Orion's belt, it is one of the brightest and most accessible nebulae for observers of the cosmos. It occupies an area of sky 4 times larger than that covered by the full moon. Its size is around 24 light-years, but it's its proximity to Earth that makes it so visible. The Orion Nebula also owes its shimmering colors to hot young stars that emit intense ultraviolet light. This light excites the surrounding gas, mainly hydrogen, which then glows in different visible colors, giving the nebula its characteristic brilliance. This is the case for most nebulae, which are ideal zones for the formation of star clusters. Nebulae are nothing more than vast clouds of gas and dust in space. They contain all the elements necessary for star formation. When a nebula collapses under the influence of gravity, it creates regions of concentrated matter, known as protostellar cores. These cores are dense clusters of gas and dust, with high temperatures and pressures. Under these conditions, matter continues to accumulate and collapse until nuclear reactions are triggered in the core. This event marks the birth of a new star. When a large number of protostellar cores form within a nebula, they can eventually give rise to star clusters. The stars in the cluster thus share a common origin and are often gravitationally linked to one another. There are two types of cluster. Firstly, there are open clusters. These are clusters of young bright stars that are also massive and hot. Open clusters generally contain a few dozen to a few thousand stars and are scattered over a relatively vast area. Then there are globular clusters. These are clusters composed mainly of stars that are older and less massive than those in open clusters. Globular clusters typically contain hundreds of thousands to millions of stars and are also very dense. They owe their name to their spherical structure, which gives them a globular appearance. In the Milky Way alone, researchers have identified over 150 such clusters. One of the best known is undoubtedly M13, the large cluster in the constellation of Hercules. Located some 22,000 light-years from Earth, M13 has fascinated astronomers for centuries. Both massive and very compact, it's difficult to say exactly how many stars it contains. Estimates range from a few 100,000 to several million stars, tightly packed into a sphere, around 145 light-years in diameter. In the night sky, its apparent diameter is about half that of the full moon. The M13 cluster is also one of the oldest objects in our Milky Way. It is around 12 to 13 billion years old. It was therefore formed very early in the history of the universe, which was born around 14 billion years ago. The stars making up the Hercules cluster are predominantly low-mass, low-metallicity stars. In other words, they contain relatively small quantities of elements heavier than helium. There's also an interesting anecdote about this globular cluster. In 1974, M13 was chosen to send an interstellar message in the hope that one day an extraterrestrial civilization might receive it. Unfortunately, the chances of ever receiving a reply to this message are slim. So if there are no little green men in the Milky Way, we may have to look elsewhere. And why not in Andromeda? After all, it's the closest galaxy to us if we exclude dwarf galaxies. Located around 2.5 million light-years from Earth, Andromeda and the Milky Way appear to be closing in on each other at high speed. So much so that one day the two will collide to form a huge elliptical galaxy called Milky Way. But rest assured, this won't happen for another 4 billion years. The Milky Way has a radius of around 52,850 light-years. Andromeda, on the other hand, has a radius of almost 110,000 light-years. It would contain around 1,000 billion stars. That's 2 to 5 times more than our own galaxy, which makes it 25% brighter than our beloved Milky Way. And yet, despite its impressive dimensions, Andromeda pales in comparison to the largest galaxy known to date, IC 1101. IC 1101 is a monstrous elliptical galaxy in the farthest reaches of the cosmos, 1 billion light-years away. Its diameter, mind you, is 6 million light-years. It's also home to over 100,000 billion stars, giving it a mass 2,000 times greater than that of the Milky Way. It's simply unimaginable. But in February 2022, another contender emerged to challenge for the crown. This galaxy is Alcyone, a cosmic monster 16.3 million light-years long. In reality, Alcyonia is not quite a galaxy, but rather a radio galaxy. This means that it emits radiation at very specific wavelengths. Radio galaxies are characterized by their intense emission of radio radiation, which comes from their active, supermassive nuclei. They are generally divided into 2 main categories: double-lobe radio galaxies and double-jet radio galaxies. The former have a Y or X-shaped structure, with 2 symmetrical lobes on either side of the central nucleus. Each lobe is made up of matter ejected at speeds close to the speed of light. They are the result of the presence of an active supermassive black hole in the middle of the galaxy. Double-jet radio galaxies feature narrow jets of matter ejected from the central nucleus at near light speeds. But unlike double-jet radio galaxies, they have no extended lobes. In any case, the behavior of radio galaxies is thought to be due to the presence of supermassive black holes at their centers. The latter actively absorb the surrounding matter, releasing an enormous amount of energy. This then manifests itself in the form of radiation of various wavelengths, including radio waves. These radio emissions come mainly from matter heated and accelerated by relativistic particle jets in the vicinity of the central black hole. This is why radio galaxies are an important object of study in astrophysics. They provide essential information on the processes of matter accretion around supermassive black holes. They also enable us to better understand the impact of these cosmic chasms on the evolution of galaxies and the universe on a large scale. Speaking of black holes, the one at the center of Alcyonia is not as gigantic as you might think. In fact, both Alcyone's stellar mass and the mass of its supermassive black hole are lower than those of other giant radio galaxies discovered previously. That said, it is still 100 times more massive than the black hole at the center of the Milky Way. So the largest known galaxy doesn't have the biggest black hole we've ever seen. But where is it hiding? The answer lies 700 million light-years away in a supergiant elliptical galaxy, the brightest in the Abell 85 cluster. This is Holmberg 15A, also known as Holm 15A. Around 3 times larger than the Milky Way, this distant cousin harbors at its center the largest world devourer ever discovered. Not a supermassive black hole, but an ultramassive one. 40 billion solar masses. The size of the associated event horizon, the limit beyond which nothing, not even light, can escape its pull, is simply unimaginable. Nearly 800 times the distance between the Earth and the Sun, That's 10,000 times the distance to the supermassive black hole at the center of our Milky Way. So far, we've seen that there are planets, stars, galaxies, and even giant black holes. We've also seen that stars can group together to form clusters. But what you may not know is that galaxies also form clusters. They entwine along a cosmic web to form complex structures of staggering size. These are known as supergalaxy clusters. Imagine a multitude of cosmic islands made up of billions of stars, grouped together in a colossal assemblage, like pieces of an immense cosmic puzzle. That's exactly what a supercluster is. To put it more simply, it's a large-scale cosmic structure made up of multiple galaxy clusters. And the clusters themselves are groups, sometimes containing up to several thousand galaxies. Superclusters can therefore group together dozens or even hundreds of clusters, creating a structure of colossal size. These cosmic giants extend over megaparsecs, an astronomical unit of measurement equivalent to more than 3 million light-years. Gravitational force is both the driving force and the cement of these astronomical constructions. Gravity pulls galaxy clusters together, forming a compact, massive whole that spreads across the fabric of space-time. This creates an environment where galaxies of all shapes and sizes cohabit, exchanging gas and stars and interacting gravitationally. Over time, superclusters continue to assemble, constantly drawing new galaxy clusters into their orbit. They also evolve through collisions with other superclusters, creating cosmic interactions of extraordinary complexity. Their discovery and study are of crucial importance to cosmology. They help us to understand the distribution of matter in the universe, as well as the dynamic forces that shape the evolution of galaxies over time. Now let's delve into the heart of these immense structures. Let's take a closer look at one of these superclusters that particularly arouses our curiosity and admiration, Laniakea. The name Laniakea comes from the Hawaiian word for celestial immensity. It's a fitting name given the sheer size of the structure. Laniakea extends over an area around 500 million light-years in diameter. That's almost 5,000 times the size of our own Milky Way galaxy. When we speak of Laniakea, we're talking about a supercluster of galaxies, a gargantuan collection of individual groups of galaxy clusters that span vast regions of space. And at the heart of this vastness lies our own galaxy, the Milky Way. Floating like a grain of sand on the edge of an infinite beach. Every point of light you see represents billions of stars, planets, gas, and dust. From up here, Laniakea looks like a brilliant constellation, its contours defined by the movements and attractions of the galaxies that make it up. Laniakea's interior is a complex collection of galactic filaments, dense clusters, and vast voids. These filaments are in fact cosmic highways, where galaxies migrate and interact under the influence of gravitational forces. It's a complex cosmic dance, in which each participant is linked by the invisible chains of gravity. The Milky Way, with its distinctive spiral, and our neighbor, the Andromeda galaxy, are part of the Local Group, a cluster of galaxies belonging to the Virgo supercluster, itself part of Laniakea. Laniakea does not stand alone in the vastness of space. It is in constant interaction with other neighboring superclusters, such as the Perseus-Pegasus supercluster. These interactions on a cosmic scale shape the evolutionary landscape of the universe. But why are these structures so important to scientists? By studying superclusters, we can better understand how matter agglomerated after the Big Bang, and how galaxies formed and evolved. Ultimately, Laniakea is not just a supercluster of galaxies. It is a witness to cosmic evolution, a milestone in our understanding of the universe, and perhaps most importantly, our home in the great cosmos. And what's even more fascinating is that Laniakea itself is just one of many superclusters. It accounts for just 4% of the observable universe. Our celestial immensity is actually connected to other superclusters, forming even larger structures, and an eternal celestial dance orchestrated by gravity. It was by conducting these studies on very large scales that astronomers were able to identify what is to date the largest and most massive known structure in the observable universe, the Great Wall of Hercules Boreal Crown, a fitting name for this gigantic galactic filament. Discovered by chance in 2013, following a gamma-ray burst mapping program, the Great Wall of Hercules is, so to speak, a supercluster of superclusters of galaxies. It measures almost 10 billion light-years by 7.2, making it 900 million light-years thick. It contains tens of thousands of galaxies and lies 10 billion light-years from us. By way of comparison, the diameter of the observable universe is 93 billion light-years. The Great Wall of Hercules therefore represents around 10% of the observable universe. Within the wall, galaxy clusters and superclusters are interconnected by filaments of hot gas. Since its discovery, researchers believe that other, potentially even larger, similar structures lurk in the darkness of the sidereal void, waiting to be discovered. Together, they would form the great web of the universe. If, from our perspective, galaxies and matter scattered throughout the cosmos seem to be scattered randomly, in a kind of infinite chaos, galactic filaments put this vision into perspective. In the end, things seem far more orderly than they appear at first glance. A bit like atoms coming together to form molecules on a microscopic scale. Other galactic fabrics have been discovered in recent years. Such is the case of the Great Sloan Wall, which for a decade was considered the largest structure in the universe, before the Great Wall of Hercules Boreal Crown took its title. With a length of 1.3 billion light-years, it was a worthy challenger, no pun intended. It was spotted in 2003, thanks to data from the Sloan Digital Sky Survey, SDSS Spectroscopic Survey. Even more recently, Boss's Great Wall came to the fore. More modest than the previous two, it is nonetheless an impressive network, comprising 4 superclusters of galaxies. It is estimated that at least 830 galaxies are trapped in its nets, giving it a mass equivalent to 10,000 times that of our own Milky Way. As discoveries progress, the galactic fabrics or filaments known as the wall lose their anomalous status. On the contrary, these formations are as widespread as stellar or planetary systems within galaxies. In fact, there are even stranger cosmic formations than clusters or walls. They're called superstellar bubbles. These are enormous cavities or spherical structures scattered throughout the interstellar medium, Stellar superbubbles are created by the explosive activity of multiple massive stars, notably supernovae and stellar winds. Supernovae are cataclysmic explosions that occur when a massive star exhausts its nuclear fuel and collapses in on itself, releasing a colossal amount of energy. Stellar winds, on the other hand, are constant ejections of matter from the surface of massive stars during their active life. Massive stars eject large quantities of matter, energy, and particles at high speed during their explosion and aging phases. The formation of superbubbles begins when these giants reach the end of their life cycle. These phenomena expel matter and energy into the surrounding space. If several massive stars form in a given region of a galaxy, their combined explosions and ejections can create a huge cavity in the interstellar medium, forming a stellar superbubble. Inside these superbubbles, the gas expelled by the stars mixes with the surrounding interstellar gas, creating dense, hot regions. The shock waves generated by the explosions propagate through the interstellar medium, compressing the surrounding matter and promoting the birth of new stars. Superbubbles can extend over hundreds to thousands of light years. They are therefore just one of the many forms that large-scale cosmic structures can take. Once again, they reflect the diversity of phenomena and creative processes that can take place within our universe. Magnificent cataclysms which give rise to the most terrifying explosions, but also to the most beautiful creations that man can observe. Far, far away, lost on our blue planet, we'll continue to scan the skies in search of these events that are beyond our comprehension in an attempt to unravel their secrets. Ridiculous as we are in the face of cosmic immensity, our thirst for discovery, but perhaps also our natural ego, leads us to believe that one day infinity will reveal its secrets to us. Throughout our journey, we've been able to admire many of the cosmic immensities that dot our universe. But however large and imposing these entities may be, they all remain measurable. This raises a crucial question. Does the universe have an end? Is it just a huge bubble filled with galaxies, stars, black holes, and other stellar objects? And if so, what surrounds this bubble? Is it nothingness or something even more vast? As soon as we take the slightest interest in the cosmos, all these dizzying questions inevitably come to mind, to the point of making us feel uneasy, because these questions confront us with the limits of our own understanding. We may understand the principle of infinity, but we can't visualize it clearly in our minds. It's as if we're missing some key to understanding. An emptiness that means we can't put our finger precisely on certain concepts to grasp all their nuances. And then comes the ultimate question. Are the secrets of the universe meant to be understood by man? Or are they, by their very nature, forever inaccessible to us? Taking the thought process a step further, we might even wonder whether understanding all the workings of the world around us would make our existence more meaningful. After all, isn't it this perpetual lack of understanding and the mysteries that lie before us that drive us to live to discover them? It's up to you to find the answer. Perhaps it will lead you to other questions, which will continue to fuel the flame of your curiosity. That burning desire to seek the truth, to understand how things work. But first, what exactly is a supercluster? We know that galaxies tend to cluster together, in groups of a few dozen galaxies, or in clusters of thousands. These groups and clusters of galaxies will themselves group together to form superclusters. Superclusters are gigantic groups of galaxies, sometimes hundreds of millions of light-years across. Each supercluster contains dozens of galaxy groups and clusters. In the Virgo supercluster, for example, we find the local group, the group of galaxies that hosts our own Milky Way, as well as galaxy clusters such as the Virgo cluster and the Furnace cluster. The Virgo supercluster is the best-known supercluster because it's the one we're in, but it's not the only one. The nearest supercluster is the Hydra Centaur supercluster, which groups together two superclusters, the Centaur supercluster and the Hydra supercluster, separated by 150 to 200 million light-years. The Shapley supercluster is another well-known supercluster located 650 million light-years away in the Centaur constellation. Superclusters are interesting for astronomers because it is on their scale that we can see the expansion of the universe. The expansion of the universe is the phenomenon whereby the objects that make up the universe on a large scale are moving away from each other. This is not, as we might think, the movement of galaxies away from each other, but a dilation of space. The expansion of the universe is the solution found by Russian physicist and mathematician Alexander Friedmann to explain why the universe has not yet collapsed under the effect of gravitation. When we observe large-scale celestial objects, such as superclusters of galaxies, this expansion translates into an increase in the wavelength of the light emitted by the galaxies. This is known as the redshift. In contrast, the blue shift is the decrease in the wavelength of light emitted by galaxies. The redshift reflects the apparent distance of celestial objects, while the blue shift reflects their approach. The expansion of the universe is not visible on the scale of galaxy groups or clusters. In galaxy groups and clusters, galaxies are gravitationally bound together, with a gravitational force strong enough to resist the expansion of the universe. But in the case of superclusters, the gravitational force is not strong enough, and the expansion of the universe makes itself felt. Clusters of galaxies are moving away from each other, albeit very slowly, but this is enough to increase the size of galaxy superclusters over time. For example, the local group is approaching the Virgo cluster at a speed of several hundred kilometers per second or miles per second. Superclusters are of interest to scientists not only because they enable them to study the expansion of the universe, but also because they help them to understand the organization of matter in space. To study the structure of galaxy clusters, scientists have developed a method based on Hubble-Lemaitre's law. This method reveals the actual distribution of clusters in the universe, without the results being distorted by projection effects. Hubble-Lemaitre's law has made it possible to measure the distance to very distant objects. This law states that galaxies in the observable universe move away from each other at a speed roughly proportional to their distance. This means that the further away a galaxy is from us, the faster it seems to be moving away. To measure the distance of distant objects using Hubble-Lemaitre's law, scientists first perform a spectral analysis of the light emitted by the celestial body under observation. They then determine its redshift, before deducing its recession velocity, i.e. the speed at which the object is moving away from an observer due to the expansion of the universe. Scientists then use the recession velocity to calculate the distance to the object under study. While all this may sound simple, it can be very complicated with distant galaxies that reflect very little light. It can be difficult to obtain a spectrum of good enough quality to be usable. In any case, scientists have discovered that the distribution of matter on a large scale remains rather inhomogeneous. In other words, the superclusters are not evenly distributed, and there are huge gaps between some superclusters, which are spaces without galaxy clusters spanning several hundred million light-years. Astronomers have come to the conclusion that there are over 90% voids in the universe, and that galaxy superclusters are at the border between these voids, rather than the other way around. In fact, galaxy superclusters cluster together in filaments that form the contours of these vacuum bubbles. This reveals that the structure of the universe is far more complex than previously imagined. The origin of this structure is one of the questions that most fascinates today's astronomers, and they're hoping to get some answers thanks to the observation of superclusters. To explore the Virgo supercluster, we have to leave our solar system, then our Milky Way galaxy, then the local group, the group of galaxies in which the Milky Way lies. The local group is one of the groups of galaxies that make up the Virgo supercluster. We are now at the heart of this supercluster, some 200 million light-years across. The Virgo supercluster is also known as the local supercluster. It's called the Virgo supercluster because it contains the Virgo cluster at its center. The Virgo cluster is located around 65 million light-years from us. The discovery of the Virgo supercluster was a gradual process. In 1863, William and John Herschel published the first major collection of nebulae, revealing that a large number lay in the region of the Virgo constellation. Nearly a century later, the Franco-American astronomer G.H. de Vaucouleurs then hypothesized that this excess of nebulae was in fact a galaxy-like structure, but on a larger scale. In 1953, he called this structure a local supercluster, and in 1958, a local supercluster. In the 1960s and 1970s, the scientific community was not yet unanimous on the nature of this structure, which could just as well be a random alignment of galaxies as an ordered structure. In the 1970s and 1980s, a redshift analysis showed that it was indeed a structure. The mass of the local supercluster was estimated at 10 to the 15th power solar masses. Much of this would be dark matter, since the supercluster's luminosity seems very low in relation to the number of stars in it. Contrary to long-held belief, the Virgo supercluster is not a gravitational structure with a clear boundary. In fact, the galaxies in this supercluster are not gravitationally attracted to the center of the structure, the Virgo cluster. Instead, they are attracted to a strange object outside this structure called the Great Attractor. We'll come back to this at the end of our journey. Incidentally, the Virgo supercluster is only a portion of a larger whole called Laniakea. Superclusters therefore appear to be structures of galaxies attracted to a large attractor, rather than structures of galaxies gravitationally bound together. Let's take a moment to study the structure of the Virgo supercluster before exploring its galaxies. In 1982, American astrophysicist Brent Tully illustrated the basic structure of the local supercluster. It would consist of a disk and a halo. The disk is roughly the flattened shape of a pancake and contains 2/3, or around 60%, of the supercluster's luminous galaxies. It includes 3 galaxy cluster subgroups: the Virgo cluster, the Hound cloud, and the Virgo II cloud. The halo comprises 1/3 of the remaining elements, including many elongated objects. It's a more or less spherical halogen atom. The eastern local supercluster has no high-density nucleus. Where is the local group, and therefore our galaxy, located in this immense structure? The local group is located near the edge of the supercluster, in a small filament. It is attracted by the Virgo cluster, not the center of the supercluster. We're now going to look at the galaxies in the local supercluster. Astronomers have noticed that the elements of this supercluster are not arranged randomly. The density of galaxies decreases with the square of the distance from its center, located near the Virgo cluster. The majority of bright galaxies, i.e. those with an absolute magnitude greater than -13, are concentrated in just a few clouds. In fact, just 11 clouds concentrate 98% of the bright galaxies, including the Hound cloud, the Virgo cluster, Virgo groups 2 and 3, and Leo group 2. All in all, there are some 10,000 galaxies in the local supercluster, spread across some 100 clusters. Let's begin our journey into the heart of the Virgo supercluster by exploring the local group, where our galaxy is located. The local group is located on the outskirts of the Virgo supercluster. It comprises more than 50 galaxies. It is not possible to determine with certainty the number of galaxies in this group, as some are very faint and therefore difficult to detect, and the boundaries of the local group are not yet precisely defined. It is estimated to extend over a diameter of around 10 million light-years. In fact, it's considered a small structure, even if this may surprise you. So there could be far more than 50 galaxies in the local group, perhaps 60 or 80. What we do know is that the local group is organized around 2 spiral galaxies, the Andromeda Galaxy, or M31, and the Milky Way. Each of these 2 spiral galaxies is surrounded by satellite galaxies. For example, the galaxy closest to the Milky Way is the Great Dog Galaxy, located just 25,000 light-years from our own galaxy. A 3rd spiral galaxy has been observed in the local group, the Triangle Galaxy, or M33. It is considered a satellite galaxy of the Andromeda Galaxy. In the local group, you can also observe 2 Magellanic spiral galaxies, i.e., single-armed spiral galaxies, the Large Magellanic Cloud and NGC 3109. These galaxies are smaller than ordinary or barred spiral galaxies. You can also observe an elliptical galaxy, M32, also a satellite of the Andromeda Galaxy. Elliptical galaxies contain only old stars, so according to astrophysicists, they are the result of the collision of 2 spiral galaxies. The local group also contains 2 dwarf elliptical galaxies, M110 and NGC 147. All the other galaxies in the local group are either spheroidal dwarf galaxies or irregular galaxies. Spheroidal dwarf galaxies are small, more or less spherical galaxies, often found in galaxy clusters. They are ancient galaxies that closely resemble globular clusters. Irregular galaxies, on the other hand, are neither spherical, elliptical, nor spiral-shaped. They are very luminous, rich in bright stars, but often too small to be easily detected. According to astronomers, they were once very numerous in the universe, but collisions have reduced their numbers. As a result, they now make up just 10% of the galaxies in the observable universe. Let's take a look at the Andromeda Galaxy, the largest galaxy in the local group. With a diameter of 220,000 light-years, it is larger than the Milky Way. It contains 2 to 5 times as many stars as the Milky Way, i.e., around 1,000 billion stars. As a result, it is 25% brighter than our own galaxy. But perhaps this won't last, as the Milky Way's star formation rate is 3 to 5 times higher than that of the largest galaxy in the local group. The Andromeda Galaxy is located in the Andromeda constellation, 2.55 million years from us. You can observe it with a naked eye from the northern hemisphere. It is thought to have been formed by the collision of 2 galaxies not so long ago. Astronomers estimate its formation date at less than 3 billion years ago, at a time when the Earth already existed. The Andromeda Galaxy and the Milky Way are approaching each other and will collide in around 4.5 billion years' time. The 2 galaxies will then merge to form a giant elliptical galaxy, along with their 2 central, supermassive black holes. The Andromeda Galaxy includes numerous satellite galaxies, notably the Triangulum Galaxy, the 3rd largest galaxy in the local group. The 2 are separated by a distance of 750,000 light-years. This galaxy is unusual in that it has an HII region at its center, rather than a supermassive black hole, which is the most powerful X-ray source in the local group. The Milky Way, the 2nd largest galaxy in the local group, is home to between 200 and 400 billion stars and over 100 billion planets. The solar system is located on the periphery of the galaxy's center, the supermassive black hole, Sagittarius A, precisely 27,000 light-years away. It's interesting to note that the Sun takes around 250 light-years to circle the center of the galaxy, so it's only been around 20 times since it came into existence. Our galaxy formed longer ago than the Andromeda Galaxy. Astronomers estimate its formation at 800 million years after the Big Bang. The oldest star in the Milky Way, HE 1523-0901, is thought to have formed shortly after the Big Bang, 13.2 billion years ago. Among the Milky Way's satellites is the Big Dog dwarf galaxy, the closest to us, located just 25,000 light-years away. This irregular dwarf galaxy contains just 1% of the Milky Way's stars and is being blown to smithereens by the tidal forces of the Milky Way. It is very likely that in the future it will disintegrate completely. The closest group of galaxies to the local group is the Sculptor group or Sculptor filament. This group includes the irregular galaxy NGC 55 and the spiral galaxies NGC 247, NGC 253, NGC 300, and NGC 7793. All are very bright, although you won't be able to see them with the naked eye from Earth. Irregular galaxy NGC 55 lies at the boundary between the Sculptor filament and the local group, and is therefore the closest to us, at a distance of around 6 million light-years. It contains many stars in formation. NGC 253 is the dominant galaxy in the Sculptor filament, being the largest and brightest. You may have already seen the image taken by ESO's VISTA telescope at the Paranal Observatory in Chile. This image is impressive for its sharpness and precision. It's probably the most detailed wide-field image ever made of the Sculptor's filament. VISTA can see through the dust thanks to its infrared vision, resulting in a sharp, precise image. NGC 253 is also known as the silver dollar or silver coin galaxy. It is an intermediate spiral galaxy located in the southern constellation of the Sculptor, around 11 million light-years from us. It was discovered by German-English astronomer Caroline Herschel in 1783, while searching for comets. From Earth, you can observe it with binoculars, as it's one of the brightest galaxies in the sky after our neighbor Andromeda. You can see it from the edge and make out its spiral arms and luminous core. NGC 253 is a good example of a starburst galaxy, i.e., a galaxy that is forming stars at a high rate. This process was probably triggered by numerous supernova explosions. In fact, you can see many bright clusters scattered around the galaxy. They're a kind of star nursery. You can see very young, hot stars that have just ignited, baby stars as it were. In the famous photo of NGC 253, we can clearly see that the radiation from these newly formed stars makes the surrounding clouds of ionized hydrogen glow. NGC 247 is also part of the Sculptor group. It is a faintly barred intermediate spiral galaxy in the Whale constellation. It was discovered by the German-British astronomer William Herschel in 1784, the brother of Caroline Herschel, who discovered the Sculptor galaxy. This galaxy is relatively unknown, as it is rather difficult to observe and photograph. A large instrument would be needed to obtain an image with enough contrast to clearly distinguish the galaxy. NGC 7793 is also a spiral galaxy in the Sculptor filament and the Sculptor constellation. It is one of the brightest galaxies in the group. Studies carried out by the Chandra Space Telescope have shown that this galaxy contains 22 X-ray sources, the majority of which are located in the Eastern Hemisphere. This may be explained by interaction with a nearby galaxy in the past. Before we set off to discover another group of galaxies close to our local group in the Virgo supercluster, let's take a look at the Sculptor dwarf galaxy, which was the first spheroidal dwarf galaxy to be discovered orbiting the Milky Way. Long thought to be part of the Sculptor filament, it is now considered a satellite galaxy of the Milky Way. It is thought to be located around 280,000 light-years from Earth, but was only discovered relatively late, due to its low luminosity. The galaxy contains stars that are poor in heavy elements and therefore old. It is therefore an interesting galaxy for astronomers, as it may reveal valuable clues to the history of the earliest periods of star formation in spheroidal dwarf galaxies. We will now explore the IC 342 Maphai group, another group of galaxies close to the local group. Like our galaxy group, it is organized around two substructures made up of massive galaxies, IC 342, and the pair formed by the two galaxies, Mephi 1 and Mephi 2. IC 342, also known as Caldwell 5, is an intermediate spiral galaxy located 11.4 million light-years from us in the Giraffe constellation. It is the most luminous and massive galaxy in the group. It was discovered in the 1890s. Like NGC 253, it is a star-forming galaxy. The IC 342 subgroup includes 9 known satellite galaxies, including NG 1560, the Giraffe A galaxy, also known as Camelopardalis A or Cam-A, and the Giraffe B galaxy, also known as Camelopardalis B or Cam-B. Mephi 1 and Mephi 2 are located in the constellation Cassiopeia. They were discovered rather late by Italian astronomer Paolo Mephi in 1968. Their discovery was not easy, as they were both hidden behind the plane of our galaxy and therefore partly obscured by interstellar matter. Mephi 1 is the closest of the large elliptical galaxies to us, while Mephi 2 is a spiral galaxy with a very pronounced bar. Like IC 342, the Mephi 1 and Mephi 2 pair has 9 known satellite galaxies, including Dwingaloo 1 and Dwingaloo 2, a barred spiral galaxy and its satellite, a small irregular galaxy. Both are located in the Cassiopeia constellation and were discovered late in 1994. Indeed, they are located at very low galactic latitude, in the avoidance zone, i.e. the area of the sky that is heavily obscured by the dust of the Milky Way. We're now in the Big Dipper. What you're looking at is the group formed by the galaxy pair M81, M82, and NGC 2403. M81 and M82 were discovered in 1774 by German astronomer Johann Elert Bode. Spiral galaxy M81 is the largest of the group, with a diameter of around 87,000 light-years. Although it can't be seen with the naked eye from Earth, it remains one of the brightest galaxies in the sky, which you can observe with binoculars. M82, also known as the Cigar Galaxy, is also a spiral galaxy. It is 5 times brighter than the Milky Way, and even 100 times brighter at its center. And with good reason. M82 is a veritable nursery of stars. A few million years ago, it is thought to have brushed against M81, triggering a huge wave of star formation in this galaxy. It's the closest star-forming galaxy to Earth, so it's much studied by astronomers. It was also in this galaxy that astronomers discovered the brightest pulsar known to date, the ultra-luminous X-ray source M82X2, in 2014. M82X2 is located 12 million light-years from Earth and emits an energy equivalent to 10 million times that of the Sun. M81 and M82 are in close gravitational interaction with NGC 3077, causing the formation of atomic hydrogen filaments between these galaxies. NGC 2403 is the second most important galaxy in the M81 group. It is an intermediate spiral galaxy discovered in 1788. Half the size of the Milky Way, it is home to numerous star-forming nebulae. You can clearly see its spiral arms, as well as small spots resembling star clusters. This was the first galaxy outside our local group in which a Cepheid was discovered. Cepheids are giant variable stars, or yellow supergiants, 4 to 15 times more massive than the Sun, and 100 to 30,000 times more luminous. 2 supernovas 16 times more luminous than average were also detected in this galaxy in late 2004. At that time, the galaxy's luminosity was more than 500 million times that of the Sun. The M101 group lies between the Big Dipper and Hound constellations. It is centered on the galaxy M101, the closest of the giant spiral galaxies, and contains at least 80 galaxies. M101 has a diameter of over 250,000 light-years, twice that of the Milky Way. It is one of the 10 largest galaxies in the Virgo supercluster. It is also known as the Windmill Galaxy, or NGC 5457. Viewed from the front, when he discovered it, astronomer Pierre McCain described it as a starless nebula, very dark and very large. Yet M101 is said to contain 1,000 billion stars, 10 times more than the Milky Way. This group of galaxies also includes M51, or the Whirlpool Galaxy. M51 has recently moved closer to the galaxy NGC 5195, scattering billions of stars from NGC 5195 into intergalactic space and accentuating M51's spiral arms. NGC 5474 is also in the M101 group and may have collided with this galaxy in its recent history. It is a deformed spiral galaxy. Its nucleus is now very far from the center of its disk. NGC 5204 is a small, Magellanic spiral galaxy that emits a very powerful, ultraluminous X-ray source, discovered in 1980 by the Einstein Observatory, whose origin has yet to be identified. It could be an intermediate mass black hole. Finally, the group also includes the intermediate spiral galaxy NGC 5585, which has the particularity of having a much higher proportion of dark matter than other galaxies of the same type. We're now in the Centaur constellation. In front of you is the lenticular galaxy Centaurus A, or NGC 5128. It's the 5th brightest galaxy in our sky, and one of the closest radio galaxies to Earth. As a reminder, a radio galaxy is one in which most of the energy emitted comes from radio waves, rather than the usual components of a galaxy, such as stars, dust, or interstellar gas. Astronomers are therefore carefully studying its active galactic nucleus. In radio waves, Centaurus A extends over 20 times the apparent diameter of the Moon. Observations of this galaxy suggest that it swallowed a spiral galaxy around 500 million years ago, which would explain its intense radio emissions. Centaurus A's appearance is so strange that it wasn't until 1952 that it was classified as a galaxy. Seen from Earth, it resembles a lenticular or elliptical galaxy with a band of dust superimposed. Again, this strange morphology can be explained by the merging of 2 smaller galaxies in the past. While the bulge of the galaxy contains mainly old red stars, the disk contains over 100 star-forming regions. The Centaurus A galaxy forms a galactic group with the 2 spiral galaxies, M83 and NGC 4945. M83 is located in the Hydra constellation and is often nicknamed the Southern Windmill Galaxy for its resemblance to M101. At its heart lies a star-forming outburst region, which is disrupted by a supermassive black hole, that ingests huge quantities of matter while expelling matter and energy outwards. This is the galaxy that gave its name to the French electronic music group M83. As for NGC 4945, it's a barred spiral galaxy in the constellation Centauri that resembles the Milky Way. There are a few differences, however, which observations have revealed despite the galaxy being viewed from the edge. Its center is much brighter than that of the Milky Way, and it is believed to house a supermassive black hole that also ejects energy into space, while devouring huge quantities of matter. It has a highly active nucleus, meaning that its central bulge emits more energy than quieter galaxies. It is therefore classified as a Seyfert galaxy. We now turn to a spiral galaxy in the Peacock constellation, NGC 6744. It is accompanied by an irregular companion galaxy, NGC 6744A, which superficially resembles one of the Magellanic Clouds. Located 30 million light-years from us, NGC 6744 is considered to be a look-alike of our own Milky Way, although its diameter is twice that of our galaxy. It is one of the largest and closest spiral galaxies to Earth. Its apparent size in the sky is 2/3 the size of the full moon. Like the Milky Way, NGC 6744 has a dense, elongated central nucleus, a disk of dust, and spiral arms. Astronomers have identified at least 6 galaxies that belong to the same group as NGC 6744. Our discovery of the Virgo supercluster continues with the galaxy NGC 7582. This spiral galaxy lies around 70 million light-years from Earth, in the constellation of the Crane. This galaxy was photographed by the MUSE instrument on ESO's Very Large Telescope to study the effect of an active black hole on star formation in a galaxy. Indeed, the central black hole of NGC 7582 feeds an active core thanks to the enormous quantities of energy it releases. The study of NGC 7582 shows that a structure surrounds the central supermassive black hole, diverting the flow of energy from the active core in the form of powerful winds to protect the rest of the galaxy. NGC 7582 is considered a variable active galaxy. In 1998, a sudden and unusual change in its optical emission line spectrum was observed for several months. Among the hypotheses put forward to explain this variation, astronomers considered the capture of a star by the supermassive black hole. Today, however, it is thought to be molecular material orbiting the active center, periodically occulting it, which gives rise to these variations. NGC 7582 is also thought to be a star-forming galaxy, with one strong burst occurring 6 million years ago and another 1 billion years ago. NGC 7582 is part of the Crane Quartet with 3 other galaxies, NGC 7599, NGC 7590, and NGC 7552. We're now in the constellation of Perseus. You're looking at the barred lenticular galaxy NGC 1023, discovered in 1786 by William Herschel. It's one of the brightest galaxies to be seen, just outside the Milky Way. With a diameter of around 60,000 light-years, it contains a supermassive black hole of around 44 million solar masses at its center. It's small enough to be difficult to see from Earth. You'd need a small telescope, a clear pollution-free sky, and a time when the moon is faint or distant. The NGC 1023 group includes at least 19 galaxies in the Perseus, Andromeda, and Triangulum constellations. Most of these galaxies are either small spiral galaxies or dwarf galaxies. For example, spiral galaxy NGC 891 is the largest galaxy in the NGC 1023 group, with a diameter of 131,000 light-years. Seen from the edge, this galaxy in the Andromeda constellation is best known to astronomers for being the site of one of the brightest supernovas ever observed, SN 1986J. This supernova, discovered on August 21, 1986, had an apparent magnitude of 14. The Virgo cluster is located at the center of the local supercluster. According to astronomers, it is the largest group of galaxies within a radius of 100 million light-years. The cluster is thought to contain between 1,300 and 2,000 galaxies, including 150 large galaxies and a large majority of dwarf galaxies. The diameter of the Virgo cluster is 15 million light-years. Even the local group is smaller than the Virgo cluster and is gravitationally attracted to it. The Virgo cluster is organized around three main subclusters formed by the galaxies M87, M86, and M49. M87 is the largest galaxy in the cluster, with a diameter of 120,000 light-years. This giant elliptical galaxy contains over 10 billion stars, a supermassive black hole of 6.5 billion solar masses, and more than 10,000 globular clusters. M87 is surrounded by numerous satellite galaxies, including M98, M99, and M100, and the pair of galaxies known as the I galaxy. As for the elliptical galaxy M86, it has the particularity of approaching the Milky Way at high speed. In fact, it's the second fastest approaching galaxy after M90, at a speed of 227 kilometers per second, or 140 miles per second, according to the NED database. It is also said to contain almost 3,800 globular clusters. Finally, the third major elliptical galaxy in the Virgo cluster is M49. It's smaller than M87, but still quite large, with a diameter of 124,000 light-years. Far from the cluster's center, it is nevertheless the brightest galaxy, and therefore the first to have been discovered in the Virgo cluster. It contains some 200 billion stars and 6,300 globular clusters. The M49 group contains more than 120 galaxies in the Virgo and Bernice constellations, including the elliptical galaxy M60, which astronomers believe could constitute a fourth subcluster in its own right. In the Big Dipper constellation on the flank of the Virgo cluster, we find a group of galaxies known as the Big Dipper cluster or Big Dipper group. Its luminosity is 30% that of the Virgo cluster, and its mass only 5%. This cluster forms a ribbon of galaxies in the northern hemisphere, most of which are spiral galaxies. The Big Dipper cluster is made up of two main groups. Ursa Major North comprises most of the cluster's large galaxies, located above 50 degrees north. This boundary remains rather arbitrary. The three brightest galaxies in the Ursa Major North Group are NGC 3631, NGC 3953, NGC 4088, and M109. But these are not the only bright galaxies in the group. There are 32 galaxies with a diameter of over 30,000 light-years in this group. The second group in the Big Dipper cluster is Ursa Major Sud. Schematically, this group comprises galaxies located south of 50 degrees. The three brightest galaxies in the Ursa Major South group are NGC 3675, NGC 3726, and NGC 3938. The Virgo 2 groups are long filaments of galaxies stretching southwards from the edge of the Virgo cluster. In fact, they are a kind of extension of this gigantic cluster of galaxies. The Virgo 2 group begins at the level of the M61 and NGC 4753 groups, which form the southern edge of the Virgo cluster. The filament then passes through NGC 4697 and NGC 4699. It ends 30 million light-years further on, with a group of galaxies centered on NGC 5084, a huge lenticular galaxy seen from the edge. M61 is one of the most remarkable galaxies in this long filament of galaxies. Located on the southern edge of the Virgo cluster, this spiral galaxy seen from the front was discovered by Italian astronomer Barnaba Oriani in 1779 and observed on the same day by Messier, who initially mistook it for a comet. It is also one of the largest galaxies in the Virgo cluster. It is also a star-forming galaxy. 8 supernovae have been discovered in this galaxy to date, the latest in May 2020. The M61 group comprises at least 32 galaxies. NGC 5084 is another remarkable galaxy in the Virgo 2 groups. With a diameter of between 250 and 300 million light-years, this lenticular galaxy is gigantic. In fact, it's one of the most massive galaxies in the Virgo supercluster. Its mass is more than 10 times that of our own Milky Way galaxy. The Virgo 3 groups form a long chain of galaxy groups to the left of the Virgo cluster. It spans more than 40 million light-years. Why such a long distance? It seems that the gravitational pull of the Virgo cluster has contributed to the stretching of this chain of galaxy groups. Astronomers have estimated that the Virgo 3 cluster comprises 8 galaxy groups and 13 galaxies outside these groups. Among the galaxies in the Virgo 3 groups is the spiral galaxy NGC 5248, which is one of the brightest in its region, and the brightest in a small group of galaxies. It has a special feature that has been observed by the Hubble Space Telescope. Around its nucleus are not one, but 2 star-forming disks. NGC 5364 is a spiral galaxy with very long spiral arms. This feature allows it to be classified as a grand-style spiral galaxy, a title deserved by only a tenth of spiral galaxies. This galaxy is beautiful to look at, even if its spiral arms are slightly asymmetrical and distorted, certainly due to interactions with a nearby neighboring galaxy. Let's continue our exploration of the Virgo supercluster with the elliptical galaxy NGC 4697, located in the Virgo constellation some 40 million light-years from Earth. NGC 4697 is an active galaxy with a faint core. According to a 2008 study, it contains a supermassive black hole of around 170 million solar masses. It is also home to numerous X-ray sources and is surrounded by a halo of hot gas. These characteristics suggest that this galaxy has had a turbulent past, with supernovae, black holes, and neutron stars belonging to binary star systems, all of which could be the origin of X-ray sources. In fact, a large number of X-ray binaries have been discovered in the galaxy's globular clusters. What's more, since black holes and neutron stars are the final stages in the life of a massive star, astronomers believe that this galaxy was home to many massive stars in the past. The NGC 4697 group includes at least 19 galaxies, including the barred spiral galaxy, NGC 4731, which measures over 80,000 light-years across. Its spiral arms contain a large number of young blue star clusters. You may notice that its spiral arms are distorted. This is due to interaction with a giant elliptical galaxy called NGC 4697. In the NGC 4697 group, you can also see a small spiral galaxy called NGC 4775, which also has deformed spiral arms, in addition to an off-center nucleus, and the barred spiral galaxies NGC 4941 and NGC 4948. In the Hound Dog constellation, you can see a vast spiral galaxy whose nucleus is surrounded by a star-forming disk. This is NGC 5033. This magnificent galaxy would have a perfect shape if it hadn't crossed paths with another galaxy during its history, slightly distorting its spiral arms. Its active Seyfert-type galactic nucleus is particularly bright, and is certainly home to a supermassive black hole that absorbs large quantities of matter. The brightness would then be due to the hot gas in the black hole's environment. Observations of this galaxy have shown that the location of the active core does not correspond with the galaxy's kinematic center, i.e. the point around which the galaxy's stars revolve. This would mean that the galaxy has certainly undergone a merger. This shift is certainly the primary cause of the core's brightness. Indeed, the shift between the nucleus and the kinematic center can destabilize the rotation of the gas at the galaxy's center, causing the gas to fall into the nucleus. The gas is then compressed by the enormous gravitational forces of the core center and becomes hot. NGC 5033 forms a pair with another galaxy called NGC 5005, but they are not close enough together for gravitational interaction to cause tidal forces and distort the galaxies. The gravitational interaction between these two galaxies remains fairly weak. In any case, we know that NGC 5033 is part of the NGC 5005 group, along with other galaxies. Astronomers disagree on the number of galaxies in this group, but there could be between 4 and 16 members. Let's continue our exciting journey into the heart of the Virgo supercluster with an exploration of the Hunting Dog Cloud. Also known as the Dogs 1 group, the Canes 1 group, or the M94 group. This cluster of galaxies spans the constellations of the Hounds and Bernice's Hare. It doesn't contain many noteworthy galaxies, so it's only very recently that we've been able to distinguish this group from the many other background galaxies in this region of the sky. In fact, it contains mostly medium-sized dwarf galaxies, ranging from 5 to 25,000 light-years in diameter. The largest galaxy in the Canes 1 group is the spiral galaxy NGC 4244, with a diameter of 65,000 light-years. This galaxy is seen from the side. Spiral galaxy NGC 4395 is a good example of a Seyfert galaxy, with a very bright core and faint spiral arms. However, it remains very faint and therefore difficult to observe. In the DOG 1 group, you'll also be able to observe NGC 4214, a small, irregular, hydrogen-rich star-forming galaxy of interest to astronomers because it contains stars in various stages of formation. Observations of this galaxy have shown complex patterns of glowing hydrogen formed during the starbirth process, but also clusters of much older red supergiant stars. Before continuing our journey, let's take a look at the spiral galaxy M94, which gave its name to the DOG Group 1, also known as the M94 group. It lies at the far end of the cluster and has a diameter of 30,000 light-years. It's a star-forming galaxy that's magnificent to observe. Yes, not only is it seen from the front, but it also boasts a beautiful ring of bright blue stars and well-defined spiral arms. In any case, astronomers haven't yet tired of observing it, and are currently trying to unravel the mysteries of its starry outbursts. The Hunting Dogs cloud should not be confused with the Dogs 2 or Canes 2 group, which lies behind it. Also in the Hounds constellation, this galaxy cluster contains a remarkable galaxy, M106. Discovered by Pierre McCain in 1781, it wasn't added to Messier's catalog until 1947. And yet, this galaxy is particularly large and bright. It is 130,000 light-years across, larger than our own Milky Way. Its morphology is unusual. 2 spiral arms are clearly visible, detached from the rest of the galaxy, which is not very bright. The most precise images of this galaxy show that it may actually have 4 spiral arms. It is not known, however, whether these 2 additional arms are made up of stars or simply gas. In the same images, impressive jets of matter can be seen on either side of the nucleus, indicating that M106 is a Seyfert galaxy with an active nucleus and that it contains a particularly active supermassive black hole at its center. The galaxy NGC 4217, often presented as a companion galaxy to M106, appears smaller, but is in fact of equivalent dimensions. It's simply not as close to us as M106. However, it's not certain that it's really a companion to M106, or even that it belongs to the Canes 2 group, as some measurements estimate it to be 60 million light-years away from us, further from M106 than it is from the Milky Way. We're now in the Lion constellation. You're looking at the Leo 1 group, which is made up of 3 subgroups. On the right, the M96 subgroup, and on the left, the M66 group, and in the middle, the galaxy NGC 3489. The M96 group includes M96 and M95, 2 barred spiral galaxies, and NGC 3377, an elliptical galaxy. All 3 are particularly bright. M96 and M95 were both discovered on the same evening, March 20th, 1781, by Pierre McCain. They are slightly smaller than our own Milky Way. Both feature an inner star-forming disk close to the nucleus, whose secrets astronomers are trying to unravel. In particular, the links between these disks and the central black tower and spiral arms. Let's take a look at the M66 group. It's also known as the Lion Triplet. It includes galaxies M65, M66, and NGC 3628. Their magnitudes make them easy to observe, especially M65 and M66, which are often photographed together, making the Lion Triplet the most beautiful group of galaxies in the Lion constellation. M65 is a spiral galaxy, and M66 a barred spiral. As for NGC 3628, it's a magnificent spiral galaxy seen from the edge, with clearly visible dust bands. We can also see a trail of stars that have been torn from it by the gravitational forces between the three galaxies. In the past, interactions between NGC 3628 and M66 strongly affected the morphology of M66, which now has a more elongated spiral arm and a more diffuse halo. NGC 3489 is located in the Leo 1 group, between the two subgroups of M96 and M66. This lenticular galaxy interests astronomers for its hybrid characteristics. It has a prominent galactic bulge and a visible central disk, like spiral galaxies, but no spiral arms. It also borrows characteristics from elliptical galaxies, with little ongoing star formation and stars over 1 billion years old. Like many of the galaxies in the Virgo supercluster, it is a Seyfert galaxy with an extremely bright core and a central black hole that devours any matter approaching it. The radiation from its active galactic nucleus, however, is weaker than average. See that vast gathering of galaxies to the right of the Virgo cluster? Those are the Leo 2 groups. These groups of galaxies lie behind the Leo 1 group and are spread over 30 million light-years. The elliptical galaxy, NGC 3607, is the brightest in the Leo 2 group. Among the other brightest galaxies in this area of the sky, you'll also find NGC 3169, a highly distorted spiral galaxy. It can be seen in the Sextant constellation, just below the star Regulus in the Leo constellation. Gravitational interaction with its neighboring galaxy, NGC 3166, has taken its toll on its magnificent spiral shape, and it now looks as if it's completely disintegrating. Astronomers wouldn't be surprised if the two galaxies were to merge. In Leo groups 2, you can also observe a curiously shaped spiral galaxy, NGC 3187. It features very open spiral arms. As for spiral galaxy NGC 3227, it's glued to dwarf elliptical galaxy NGC 3226. Both are among the 338 galaxies listed in Halton Arp's Atlas of Peculiar Galaxies, under the name ARP 94. According to American astronomer Halton Arp, they are a good example of a spiral galaxy with an elliptical companion. However, there is nothing to suggest that they are in fact interacting gravitationally, especially as the distance between them remains relatively large, at around 9 million light-years. Let's continue our journey towards the Furnace Cluster. But before we do, let's take a look at a remarkable galaxy called NGC 2997. This grand-style spiral galaxy is located in the constellation of the Pneumatic Machine, a constellation you may not have heard of often since it's located in the southern hemisphere and is relatively faint. NGC 2997 was discovered by William Herschel in 1793 and lies around 55 million light-years from us, but is moving away from us at around 1,100 kilometers per second or 680 miles per second. This galaxy is particularly remarkable for its nucleus, surrounded by a string of giant clouds of ionized hot hydrogen. The NGC 2997 group comprises some 15 galaxies, including several irregular Magellanic galaxies. Before arriving at the Furnace Cluster, the Dorado group is also worth a visit. Call it a group, but it's more likely to be a cluster of galaxies given its size. The Dorado group comprises spiral and elliptical galaxies. It is organized around two interacting galaxies, the elliptical galaxy NGC 1549 and the lenticular galaxy NGC 1553. These are the two brightest galaxies after the spiral galaxy NGC 1566, considered the dominant galaxy in this group. NGC 1566 and NGC 1553 are disk galaxies, which is the dominant galaxy type in the Dorado group. Astronomers therefore consider this group to be even richer than the local group. We're now looking at the Furnace Cluster, the only other cluster within 100 million light-years of us that's almost as rich as the Virgo cluster, though still a little smaller. The Furnace Cluster is of particular interest to amateur astronomers for its compact core of galaxies spread over just 2 degrees of sky. The two dominant galaxies in the Furnace Cluster are NGC 1316 and NGC 1365. They're bigger than any galaxy in the Virgo cluster. NGC 1316 is a massive lenticular galaxy, which according to observations absorbed a spiral galaxy around 3 billion years ago. This was probably not the only galaxy to be cannibalized by NGC 1316. Not far from this galaxy is a spiral galaxy called NGC 1317, which could suffer the same fate. NGC 1316 is also a powerful radio source, known to radio astronomers as Fornax A. It is the most important source of radio waves in the constellation Furnace, and the fourth most intense radio source in the sky. These radio waves come from falling matter inside the supermassive black hole at the center of the galaxy, probably fueled by interactions with other galaxies. NGC 1365 is the best-known galaxy in the Furnace Cluster. It is a magnificent barred spiral galaxy of great style. Discovered in 1826 by Scottish astronomer James Dunlop, it lies in the southern constellation of Furnace and is studied by numerous telescopes. Its bluish color is due to a very high rate of star formation. This can be explained by the presence of a bar that connects the two spiral arms and compresses the gas present in the galaxy, triggering the birth of multiple stars. The Eridan cluster is another remarkable galaxy cluster in the southern hemisphere. It is sometimes referred to as the Furnace II cluster. This is because it is very close to the Furnace cluster at a distance of around 20 million light-years. the Eridan cluster is further away than the Furnace cluster, at around 75 million light-years. These two clusters and their surrounding galaxies are sometimes referred to as the Furnace or Deep South superclusters. The Eridan cluster contains around 200 galaxies. Its galaxies are scattered over a larger area than in the Furnace cluster, so it is less impressive than its neighbor. Two subgroups can be distinguished, one to the south around NGC 1395 and one to the north around NGC 1407. NGC 1407 is a vast elliptical galaxy, larger than the Milky Way, with a diameter of around 243,000 light-years. Its group contains at least 9 galaxies. NGC 1395 is also a vast elliptical galaxy, but slightly larger, with an estimated diameter of around 264,000 light-years. The NGC 1395 group contains at least 32 galaxies. We can't leave the Eridan cluster without a quick look at NGC 1232, one of the most beautiful galaxies in the cluster, with its well-defined spiral arms. This stylish spiral galaxy is around 145,000 light-years across, and its spiral arms contain millions of bright stars, alongside dark dust, to the delight of our eyes. We've taken a tour of the Virgo supercluster. This trip will have given you a glimpse of all the types of galaxies that exist in the observable universe, with near-perfect spiral galaxies and spiral galaxies distorted by the movements of the universe, giant galaxies and dwarf galaxies, active galaxies, and galaxies where no stars are forming anymore. But you should know that the Virgo supercluster won't remain frozen like this for long. The universe may be moving slowly, but it's moving all the same. The Virgo supercluster itself is constantly changing. It is attracted by the Great Attractor, a gravitational anomaly located near the Ruler cluster. But what exactly is the Great Attractor? The discovery of the Great Attractor dates back to 1977. American astronomer Vera Rubin and her colleagues at the Washington Institute discovered that the Milky Way was moving faster than the expansion of the universe. The astronomers hypothesized that there was a force with a gravitational effect on the Milky Way, without knowing exactly what it was. A team of 7 researchers from the Cambridge Institute of Astronomy and the Washington Institute of Astronomy was formed to investigate the question. For the record, this team was nicknamed the Seven Samurai. To unravel the mystery of this unidentified gravitational force, the researchers measured the proper velocity of a large number of galaxies in order to determine in which direction the Milky Way and the local group were moving. 400 elliptical galaxies in the Centauri region were studied over a 5-year period. In 1986, the researchers from this small team discovered that the local group, as well as the Virgo supercluster, were moving at a speed of around 625 kilometers per second, or 390 miles per second, towards a point they dubbed the Great Attractor. This point lies beyond the Hydra Centaur supercluster, in the direction of the Southern Cross, some 150 million light-years away. Scientists have calculated that the gravitational force of this mysterious attractor is equivalent to that of a supercluster, over 10,000 times the Milky Way. And yet, no visible mass has been identified. Here is a spine-chilling anecdote. Foucault's pendulum in the Pantheon in Paris points in the same direction, but no one knows why. an even more mysterious fact. In the region of the Great Attractor, the natural speed of galaxies is that of the expansion of the universe. And once past this fictitious point, galaxies have a speed slower than that of the universe's expansion, and some even show a blue shift. But the presence of the Great Attractor alone cannot explain these speed variations. In fact, other researchers have measured the radial velocities of galaxies in the Perseus and Pisces clusters, which are located further from the Great Attractor than the Milky Way. And it appears that they are drawn faster towards the Great Attractor than our galaxy or even the Centaurus or Hydra clusters located closer to this fictitious point. Researchers have put forward all kinds of hypotheses, including the presence of another Great Attractor or the imprecision of radial velocity measurements due to the uncertainty linked to galaxy luminosity. In 2016, after 30 years of research, researchers identified the existence of large extragalactic structures that could explain the gravitational attraction of galaxies towards the Great Attractor, without, however, completely solving the mystery. We've come to the end of our journey through the Virgo supercluster, but we're not done exploring the universe yet. The Virgo supercluster is part of a larger whole called Laniakea, and Laniakea itself is just one of the 6 million superclusters that exist in the observable universe. So there's still a long way to go before we understand all the mysteries of our universe and its organization. In the meantime, we can marvel at the beauty of galaxies and stars and the way they are arranged in the sky, whether by chance or not.